Hey, and welcome to SkyTour LiveStream. What do you think of that? I mean, is that not beautiful? That was one of my test images to see how well the system is performing. And as you can see, it's doing well. I want to first of all welcome Daryl Mason. Hello, Daryl. How you doing?
Hello, Tom. Hello. What's your name, Marc? Hello, Marc. I'm well. You? Hello, everybody.
I'm okay, Billy Bob. Actually,
Billy Bob is one of my brothers.
Okay.
Sorry, Tom said hi to me. Tom.
It happens. It's fine. Yeah. So it's nice to see you guys. I see a bunch of people here, and I want to say hi to them. Welcome to PG, who was first actually about an hour ago. Izabela's here with us. Nice to see you. CND boy is with us already. Hedrick, how are you, Hedrick? Nice to see you. Hedrick, you are a moderator. Congratulations. I made you a mod. That gives you magic powers, like the rest of them. You've demonstrated the sound mind and proper attitude for our channel. And hello.
Great powers comes great responsibility. That's
right. Now, it's not that others who don't have it yet don't deserve it. It's just that I'm slowly getting people in. So, hello, Daisy and Zoe Amethyst. How are you? I hope that you guys are doing well tonight. This is my first stream after returning from this observatory here, and I can't believe I was in that building just the other day. It's like, ah. Hey, Donald Kunzer, how are you? Greg O'Brien, what's going on? I haven't been to Cherry Springs Star Party. I'd like to know where it is. I asked you that, but I don't know if you answered. Maybe you have. So, Anahata 77 is here as well. Cherry Springs State Park in Potter County, PA. Very nice. I will have to look into that. One of our thrusts, if you will, with SkyTour Livestream is to create a portable roaming observatory that we tow behind an RV and set up with this kind of capability anywhere we go in the country. That's one of the things we want to do. Robin Curtis is with us. Hey there, Robin. Good to see you. And Papa Tom. So that's it for now, the ones that I see. This is the Eastern Veil Nebula. It is really pretty, and we're at 100% scale on the sensor. And as we zoom out, you can see the full extent of this magnificent maelstrom of hot ionized gas. It is just beautiful. As we've shown before, the green is oxygen 3, which is doubly ionized oxygen. The red is ionized hydrogen primarily. Now, that's not the only elements that are being ionized in these nebulae. In fact, that's not the only elements that stellar explosions that cause things like this will create. They create a whole host of other elements. It's just that the vast majority, this particular transition of oxygen to this green transition and the transition that creates the hydrogen red, those tend to be the dominant ones. So that's why we see them that way. So Greg O'Brien says breathtaking. It is breathtaking. And as you might know, if you remember where we are in the sky, this is the constellation Cygnus. Let me bring up the planetarium to show you. Back out a little bit. Okay, this is Cygnus the Swan right here. You can see when I pull in the artwork, you can see there's the the tail of the swan is Deneb, star Deneb, and the wings are these stars that cross out here on either side of the central star Sadr. And where you see the STLS icon, that is where the telescope is pointing. This is the actual location of this beautiful nebula we're looking at. And it's actually not one nebula, it's a complete spherical nebula of expansion debris from a supernova explosion, the most cataclysmic explosion that is seen in the universe besides the Killa and hypernovas above them. Down at the head of the swan is this beautiful double star called Albireo. And Albireo is a gorgeous double star. It's actually a B-type star and a K-type star. And the B stars are blue and the K stars are orange. And when you see these in the eyepiece, they're just stunning. We might take a ride down there in a little while just to check that out. But for now, I just want to bring you back to this location here. This is our focus right now. We're looking at this side of the nebula. Okay, that's where we are, and this is the side of the nebula we're going to go to and check out in a minute. All right, so if we come back into our telescopic view, you can see that we are here. All right, and we're going to head to the right a little bit. So I took 30 exposures and I saved them, and I'll save it exactly as seen now. All right, and again, this is, let me put that out there for you, this is the Eastern Veil Nebula, a supernova remnant. All right, and so what we'll do is we will now go off and check out the Western Veil and the Central Veil. All right, and then we'll move around and look at other things in Cygnus. Cygnus is a dense star cloud location because that's another arm of the Milky Way galaxy that we're starting to look into as we look away from the southern Milky Way. We look into the next spiral arm and we see the whole Cygnus region. And we keep going, we'll look into the Orion Spur and other locations there. Hello, Marco. So that should be fun. Ricardo, how are you? Oh, Ricardo says, can't wait to get a large screen TV hooked up. Your videos are so great, even on my cell phone. You know what? There are people that put these on 80-inch screens, Ricardo, and they just, like, they sit there with popcorn like it's a movie. That's kind of cool. Never thought about that, but I think it's neat. All right. So this is the Eastern Veil. So what we're going to do now is move to the Western Veil, which is right next to it. It's over here. All right, and we're going to actually center on the star near 52 Cygni. Okay, this is a filamentary nebula here. But before I tell it to go, let me just get us into our night vision mode here, because I think that would make it a lot better. Alright, and then we'll get rid of the stack. Alright, so there we are. And then we'll pop up night vision mode. I'm trying something new. In the past, I would do a waypoint star, and that would add time to the time it takes to find things. Let me pull that out. Alright, but now I'm just going to use direct coordinates, and I'm going to basically tell us to go directly to objects, and there won't be any waypoints. It's just going to go right to the objects. We're going to see how that works. If that works well, then we are going to continue to do that. Alright, so we're going over here. We're going to go to the filamentary nebula. Alright, and let me just first, there we go. Alright.
Wasn't the high precision pointing, you said, might have been the issue with
yes,
landing 10 degrees off from where it was supposed to be?
One degree.
1 degree?
Yeah. So I think I got that fixed, and we're going to see now. So we should now just go right to that nebula and not go any place in between. And there we do. There it is. See that? Much better. So this is going to be a lot nicer, and it'll be far better for us. So here's the central veil. You can start to see it even in night vision mode, and this is the Western Veil. I'm going to pull that up so you can see the entire witch's broom in here. Okay, we're going to be able to see more objects because I'm not going to have it do that waypoint side. Alright, so right here is good. Let me just move a little bit to the west.
You might sync on the star to dial in your pointing.
Yeah, I will. I could do 52 Cygni, but I want to actually start the exposure because we have a moon coming up soon. And I want to avoid that, get as much of the good stuff done before the moon comes up. But albeit it's later on in its cycle, so it's going to be waning gibbous on the way to waning last quarter. Actually, it's the last quarter. MPC 305, how you doing? The nebula is so dim because we haven't started taking pictures of it. This is just effectively our night vision finder, effectively. All right, so you can see our guiding here is taking place. You can see the numbers changing. It's stabilized. And so now you want to see it. I'm going to do a 35-second exposure, and now you're going to see a very big difference, okay? So we're going to go out. And this is our previous shot we just took a few minutes ago. See how bright that is? That's what we're going to see with this coming nebula. This one's already been saved. And as soon as we save our images, for those that may not remember, they go right up to the cloud and off to a server that you have access to right now. And to get there, you can go to SkyTourLive.com right there on the bottom. SkyTourLive.com is our entry portal. Scroll down to the next section and it'll say, take me to see great pictures. And it'll take you to the directory and you look for the date for tonight. Look at that. And wade into the directories and you'll see there's one called processed. It's all written out there on SkyTourLive.com. And then you can see the images that we take exactly as you see them here. All right. This is a beautiful nebula. Okay, let's pop that down so we can get a little more scale here. This is called the Witch's Broom, or we'll call it Daryl's Tornado, because he says it looks like a tornado.
Well,
sort of does.
There in that upper part it does.
Yeah, it does.
I know it's called the Witch's Broom.
Yeah. Now what's interesting about this is that you see these little spindles and tendrils. It's always been a mystery to us why those tendrils exist, but now there's another theory, which is possibly a good one actually. And that theory is that there's electrical charge that plays a role in shaping these tendrils and spindles that we see in these nebula. And that's very possible. And so when we zoom in and we look at these things, we have to understand that when a supernova explodes and particles go out, it's not just hot gas. It's hot gas with charged atoms in there. And that charge will in fact affect how the gas reacts to other gas particles and so forth. So this could be part of the reason why they look like this. No. Oh, Greg O'Brien says, could I see this using my SIONYX in night vision mode? I know it won't look this good. Let me first of all explain what SIONYX is. And to do that, hold on one second. Sorry. All right, hang on. Almost ran over my dog. Okay. What Greg is talking about is if he uses this right here. I actually have one of these. I'll show you. All right. This is the SIONYX. I guess it would help if I came back, huh? Let me make this happier for you, all of you. Here we go. Okay. So, this is the SIONYX camera, and it doesn't come with this cover. I added it, but this is a night vision camera that you might think, because it's full color and you look through it and you see absolutely stunning views, you might think, wow, well, this thing has got to be like thousands of dollars. No, you'd be wrong. This one I have costs $399, and it's like having an ISO 800,000 camera. That is a camera that's sensitive to with a sensitivity rating of 800,000. Most cameras can go to 6,400 and 8,000 maybe. Astronomical cameras and some of these DSLRs can go to 25,000. The Sony A7S II can go to 400,000, which is pretty cool. But this little guy, for only literally a fifth of the cost, actually a sixth of the cost of a Sony A7S II, goes to 800,000. So you can literally go outside, look in your front lawn, and see the grass as green because it's also full color. So the SIONYX, this is called the Aurora Pro. All right, the SIONYX Aurora Pro. This is the Aurora Sport, but the Aurora Pro is the one that's black, and the black case will also have a compass and GPS built in. This one does not, and it's like $200 cheaper.
Oh.
Yeah.
I should look into that. What generation night vision is that?
Well, that's the thing. There is no generation. This is all electronic. So, when you look through it at night, you'll see some noise, but it depends on the frame rate you choose. I choose 7.5 frames per second or 15 frames per second, and you can see the Orion Nebula like nothing. And it zooms in. It has zoom, digital zoom. So it's not like a generational thing like with tubes. Doesn't have a tube in it. It's all CMOS sensor.
Wow.
$399 for this guy, and that's the Sport. And the Sport does not have GPS or compass. And for $699 or $599, I forget, you can get with the additional features. It has Wi-Fi, so you can literally, if you have a Wi-Fi TV, you can take the output from this thing and put it right onto your TV and say, wow, check it out. Go put this on a tripod and aim it up in the sky and watch the meteor shower from your TV. And if you get a USB cable, it plugs in here, and that USB cable, right, that USB cable will also power it. So you'll never run out of batteries, but it does have a battery as well.
Mark, a favor?
Yeah?
Spell that for me, please.
Yeah, SIONYX is a weird name. Okay, it's spelled SIONYX, so silicon onyx, basically. SIONYX.
SIONYX.
You got it.
And the model?
This is the Aurora, and the family series is the Sport, which is the cheaper one, and then the Pro, which is the black case with green highlights. That one is the next level up, which has the compass and GPS.
Very good.
Yeah, you'll enjoy this if you get it, and I'll show you where to get this guy right here. This is a lens cap cover combo, because you don't get the cap with it. There's no lens cap with it. So you buy this VCR all-in-one lens cap, which is like all-purpose, handles all kinds of cameras. Okay, spring-loaded cap. All right, and this guy will serve the purpose of protecting this lens with no problem. For I think like $8. It's just incredible. So there you go. So there's the ad for SIONYX, and I don't even get anything from them. I should. So, all right, so we're up to 12 stacked now. Look at this. Let's just take a wander through the witch's broom. Wow. Wow, look at that. Let me go back to being mysterious. There we go. This way, if I want to come into the view, I can do so without, and pointing at all these different parts and not have to worry about having them overlaid by a background. Look at this stuff here. There's very detailed stuff right here. Look at that. That is amazing. A lot going on in this nebula. These bands might be due to shock waves of moving material that are moving out. And remember, the inside, it took place this way on this side of this, and it's heading outward like this. And speaking of those bands, just so you see that, I'm talking about these guys right here. See those right there? Those are really, those could be due to the actual shock waves of the nebula. The initial explosion.
I always, like you call that Daryl's tornado, I see especially the upper portion of that, and it just looks like a vortex, or like if there was a cloud of smoke and somebody puffed air through it or something.
It does.
Twisted like that.
It does. It looks really interesting. Let's see how close we can get in here before we've done 15 of them, so let's see. Okay, this is 175%, so we can get to see some noise here a little bit. Notice the stars are nice and round though. We got this beautiful guiding going on. Very pleased. All right, this, I'm going to come down now to, okay, this is 100% of our sensor. This is the native resolution, what it wants to be. Nice. Hedrick says, Mark, it's amazing. It goes on and on light years. Yeah, it does. It does indeed. Greg O'Brien, I'm just here for the music. That's cool. I guess I should not be. I should be quiet then, and it's like crank up the tunes then, you know. But you know, I could do both of those. Wow. This is all new music, by the way. I've replaced the. It's not replaced. I can bring it back. But I've gone to this next playlist. See what happens. Let's make this a full screen thing here. Oh, look at that. Oh. You can almost feel the heat from the ionized gas in there, you know?
Mark Hedrick says you are still in video overlay mode.
What's that mean?
I don't know. I'm just repeating what he said.
I can see that I'm not. See? Hedrick, hit refresh on your browser because you might be behind a little bit. Ah, he says, oh, that's why. Floating over pick. Yes. Okay. Grab the marshmallows, Greg. That's right. That's right. Make some s'mores with this nebula. Of course, the s'mores would, you know, the marshmallow would be melted, and the graham crackers would be incinerated.
It'd probably be glowing in the dark too.
How about no? Let's not do that. Another star right here, by the way, guys. This star is known as 52 Cygni. That guy right there. It's a foreground star. It looks very much like it's in there, and you might be tempted to think that this glow is from that star, but it's not. This star is way up here in the foreground, and the nebula is way, way back here, out here. So that's actually an illusion. The universe is full of them. Yep. This supernova remnant is roughly 8,000 years old and is about 12 to 1,400 light years away. It's fairly large. It's several full moons in diameter. It's actually a very big supernova remnant, which is why you really can't see it. You know? Now you can see, let me bring it back down here. You can see the beginnings of the central veil here. We'll go grab that next. Sorry to be scary, Hedrick, but you know what? I guess I'm just thinking of what might be logical questions that people might ask. So maybe that's why it seems like I'm reading your mind. But I assure you that I'm just having a good time. All right. Okay, we've got 22 stacks, so I'm going to go in here. The first thing I'm going to do is I'm going to bring the telescope back so I can see the telescope. There we go, it's right there. And if I'm looking left and right, guys, that's because the left side is the broadcast software and the right side is the live view from the observatory. And I've got the live view interspersed with the broadcast stuff, so I look left and right all the time. So I got 2 monitors. Soon I'll have 3, probably 6, maybe 12. It's just going to go on and on. Okay, let's come here and let's change this to Vale West. With proper name. Okay, and if you're wondering where I'm changing, that's that up there, that little box right here. I'll show you right here. I'm changing the name in this box because that's going to be the title as seen on the server when it's up there in a few minutes. Not even a few minutes, a few seconds. Okay, so Vale west is now saved up there as a raw file and saved exactly as seen as of now. So when you go up there, in literally a few seconds from now, this is what you'll see. Here's the image. There it is. That's the image you're going to get right now if you went up there. Okay, I'm using a viewer. Okay, but you can see this is what you're going to get. And of course, you could zoom in and have a lot of fun and just go to town on it and enjoy it. Make it the backdrop on your screen or on your desktop, whatever you like. You'll have lots of fun. It's all yours, all free. All right, now that we've done that, we're gonna clear this. Well, pause it first. We're gonna clear this. I'll actually save it again because we saved up to 25 at that time, and save exactly as seen. All right, now we're done. Okay, so now we'll clear this. Go back to our night vision mode here. Alright, now we're going to be in night vision mode. Whoops, I meant to be at 1 second, not 100 milliseconds. Alright. Okay. Oh, hello. I meant to close the stack. My mistake. Okay. Alright, now we got our beautiful night vision mode back. Hey, talk about night vision, huh? This is real night vision. Alright, let's go and we don't even have to do anything but just move the telescope a little bit to where we want to go next, and that place you want to go next is literally, I don't even have to do this. I can just move it from here. We're going to move a little bit to the west. All right. A little bit to the north. Like that. And we're going to catch this. This is the central veil. Now, the interesting thing about the central veil is it could be coming toward us like this or be going away from us like that, which is really cool. So we're going to put this guy right down here. This will be the tip. And we're going to move now to the east to just sort of center it up a little better. And then we can put them together in a mosaic after if we want to, because they'll fit a little further.
I see Pickering's triangle already.
It's right there. Yeah, it's the brightest part of the central veil. That's what he's talking about, guys. Ring Nebula is in Lyra, which is a little more west. We might not be able to see it too well right now. Not the ring, no. This is the central veil. It's the Greg is saying I thought it was heading to the ring. This is the central veil.
You know, if a guy really wanted to, he could keep looking at Cygnus and Vega and Lyra. I used to make it a thing every year at Christmas that if I got something new for the telescope, I'd go out and test it Christmas night or the night after Christmas.
Well, Cygnus tends to stay up later because it's just swirling around the north, but it's definitely not circumpolar, but it is definitely up long enough. Okay,
yeah.
35 seconds on this guy.
They kind of hover in the northwest as we head in.
Yeah. All right. And there we go. And now what we're going to do is go and look at the central veil. Let me clear this. So we start from scratch. The progress bar over here, you can see the yellow progress bar down there. That tells you how far we are from finishing the exposure. When it gets to here, it's done, and we'll see our image. And I do want to thank you guys for coming out here. Hello, Vids. Vids says enhance. Yeah, we would. There we go. And this is nice. Okay. Let's go to zoom mode so I can actually better see the curves. And take these and move them out. Just to give us a little bit more subtle view. Alright. You'll see in a second. Look at that. We only have one stacked, okay? We just get the second one stacked. Look at that. That is just beautiful. Wow. So Hedrick says, Mark, would a Betelgeuse supernova be blinding on that vision on this camera? It would actually create a gigantic blob like we see with the brightest stars with halos around it. Okay, so yes, it would probably be too bright for our system with these settings. I could set it up so we could look at it. Absolutely.
Saturate the sensor.
Yeah, but I can actually tone it down within the settings here. I can actually make it so that it wouldn't. See, right now our gain is at like 350, and the gain would go down to 0, and then the exposure would go down to a fraction of a millisecond, and that would be what we want. Yeah.
I think he meant that SIONYX camera, possibly.
Oh, and maybe so. Yeah, Betelgeuse would definitely saturate this, and you could tone it down a little bit, but it's really got a native sensitivity of 800,000, so it would saturate it, but it wouldn't hurt it. That's a nice thing. With the older night vision cameras, they had an actual tube in there that you could burn an image into the phosphor screen, and that it's never good because it'll never go away, and you ruin your camera that way. Okay, Hendrik. Hey, that guy, how you doing? That's a heck of an ID to manage. That guy who once twerked in the White House. That's funny. Okay, let's see if we can coax a little contrast out of this. Oh yeah. Wow, I mean, many stars. Let's zoom in now and start looking at this beautiful central veil. This looks very different from the western and eastern veils, which basically are like this. Okay, this looks like this, or this. The expanding cloud. It looks like the expanding cloud going back or towards you. And it's hard to tell which way that is or where it's going, but I'll have to look and see if there's any studies that have been done on this to show a detailed analysis of the gas directions here. The moon NPC asks, where is the moon? We'll check. The moon is going to rise at 9:30 tonight out there. It's 9:49, so technically the moon should be up right now. Let's zoom out and see.
Not from there, no.
You said 9:30.
Arizona time.
9:30 Arizona time.
Yeah.
Oh, hello. It's 7:49. I'm looking at my clock here and I'm mixing up the clocks. Okay. Yeah, so the moon will be up in a couple hours. A little less. Cosmic Ray says, Mark has enough frames of the Veil Nebula to make a full-length movie. Yeah, but it's a kind of a boring movie, Ray. right? Because it's just going to be all the same thing over and over. Except if we do a blink comparison one time to another, we might be able to see some changes long term, maybe in the fine filaments. And that would happen over many years of review. You know. Alice Pooper asks a very good question. How long before nebulas burn out? Okay, well, let's define what you might mean by burnout. They're only glowing right now because of the fact that the nebulae have gases that are being ionized. Okay, oxygen is being ionized green here, hydrogen red. Okay, so as long as these gases are still ionized, then we'll still see the gas. Otherwise, it'll be transparent, of course, because gas, you can't really see gas, right? So that is something that depends on how long these gases remain heated like this. And the question is, what's heating them? There's several different hypotheses about that. One of them is that the speed of movement through the interstellar medium is heating them up to millions of degrees and causing them to ionize. And the fact that they're colliding with other material along the way causes a resistance to motion, which also causes them to heat up. So there's that as well. The other possibility is that there is still a remnant, a soft X-ray remnant in the middle, which is actually kind of near this area. It's right around here, right around this nebula. So there might be a soft X-ray area right over here that's been identified as Cygnus X5, and that region is the one that might be illuminating some of this with X-rays and gamma rays and ultraviolet radiation. So we're not really sure, because we're really not even sure that Cygnus X5 is the actual progenitor. That's a theory.
Yeah. Some, like the Crab Nebula, it's a supernova remnant like the Veil is, but there is a visible neutron star still cooking in the center of the Crab Nebula, and that's what's, at least mostly, I guess, illuminating the crab, ionizing the crab, I should say.
Yeah, and it's also a pulsar, which means it has hot spots on this neutron star surface, which, as it spins by us, it flashes us. It's like, psh, psh, psh.
Yeah.
And it does that 33 times per second. That's pretty fast.
Yeah. And some like planetary nebulas. I don't know. I know that how far away they ionize things is a little dependent. Just a few light years, or just relatively limited with planetaries.
Yeah.
I suppose they'll stay fluorescing as long as the white dwarf in them is hot enough.
Yeah, and the white dwarf will eventually cool to what we call a black dwarf. So, first of all, I want to say hello to Alex Bronze, who's joined us. Hello. Cheryl, Texas. How are you? Cheryl, are you from Texas? I was just there yesterday, actually. I'm back in Connecticut now, but I was in Arizona teaching astronomy in the desert, and then I flew into DFW, Dallas-Fort Worth, yesterday. Saw friends there that I know, actually in the airport, flying back to Connecticut. So it was pretty cool. And then I came back to Connecticut I got in around 1 o'clock this morning. And I couldn't wait to just get going and do this stream. Just had to do it. Wait, was that this morning I got in, or yesterday? Wow. Yeah. Today's Sunday. Yeah, I got in yesterday. I mean, you know. Oh, Cheryl's in Fort Worth. Okay, that's where I was, at DFW. I flew over you. Ha ha. Good, Alex. Glad you're good. Yeah, look at this. So this is 17 stacked. We'll go up a couple more, and then we'll save it. Izabela asked a long time ago, and I missed your I missed the question. I'm sorry. Is this going to be a mosaic? Yes, you could make this into a mosaic. You should be able to link them together. If not, I'll have to take more, but I think you'll be able to do it. Cosmic Ray says, just think if Messier looked at the Veil Nebula, we would not have a Messier catalog. Or we would not have a Messier catalog? Well, I can tell you that the Veil would have been a stupendously, colossally amazing puzzle for anyone at that time to be able to see it now. Izabela, I'm composing these now. She's already doing it. Alright. We're at 18, going on to 19. That'll be good enough. Then we can move on to something new and exciting.
I dare say a Messier had a telescope capable of seeing the veil. The Messier catalog would be a whole lot bigger than it is now.
Oh yeah, without a doubt. Okay,
Probably
this is going to be...
Probably more like the size of the NGC catalog.
I'll bet. Yeah, look very different. Okay, we're going to save the central veil now. There we go. And we save that, and then we'll save it exactly as seen. Alright, and again, just to let everybody know what we're looking at, let's just put that out there for you to see. This is the central veil we're looking at right here. Okay.
Hedrick, actually we're looking about 90 degrees away from galactic center when we look towards Cygnus. Galactic center is in Sagittarius, which is setting, or is pretty much set already, down in the southwest.
Right, and then when we look toward Cassiopeia, we're looking even further away at yet another galactic arm. So we're seeing several galactic arms as we look from Sagittarius towards Cygnus and then toward Cassiopeia.
Yeah, when we look up towards Cygnus, we're looking at the next spiral arm out from us.
Yeah. And where Orion is, has been known classically as the Orion Spur. There's some controversy about that, but for now, we can just say it's the Orion Spur. Because I think there was a study done that said, spur, what do you mean spur? What's this spur stuff, you know? As you'll see. Charles Messier's favorite telescope was a 7.5 inch 104 by 104x Gregorian reflector. Yeah.
I'd have to look that up. I thought his telescope was a 4-inch refractor. I know it wasn't a very good telescope. He really couldn't see much by modern standards with it. Many of the objects he saw and put on his list of Messier objects, he just reported as nebula without stars.
Yeah. Okay, so we can clear this guy. I saved it, and now we'll clear it and move on. Whoops. All right, let's go back. All right, and let's get into night vision mode. And here we go. All right, so this is night vision mode, and we can pull this out of here because we don't want that anymore. We know what that is. All right, let's go wander through some more of the Cygnus sky. Well, since we're here, I want to take you to Albireo because I promised you I would. So let's go there now and check out this beautiful double star, which is actually, as was pointed out, I think by you, Cosmic Ray, that it was actually a visual double. Yet I thought I read a study, and I'm not sure, it's still not true, but I have to go back and find it before I finish talking about it. All right. You might be right about it. But as a visual double star, at the very least, let's take a look at this. I think this is Albireo right here. Now, the K giant, which is actually what is the orange star, is overwhelming the brightness of the B type, the late B star. Remember, they go O, B, A, F, G, K, M. And the O stars are extremely hot and blue. The B stars are very blue and hot. And then the A's, the F, G, and the K's, by the time it gets to K, they're like an orange star. All right, so let's just center this up and come back and close in on this here. All right, and let's. All right. So now we're gonna do this. We're gonna take this gain down, and there you go. We bring the gain down low, and if we stack this now, you'll find something really interesting. Actually, you know what I'll do? I'm gonna take this out and zoom in right here like this, and then play with these colors so you can actually see now. Look at this pair of stars. That's pretty. Alright, so I'm also going to take a moment to refocus because I think I could benefit from that right now. There we go. Go to night vision mode here. Okay, and let's do it. I do it once a session anyway. So we're gonna pump the focus out a bit. There we are. And then we'll go into our tools. And take a focus assistant and go to full width, half maximum. Incidentally, when you defocus a star's image, you can actually see its color much better. Notice all the different colors. You have white, you have blue, you have orange, you have red. Pretty amazing. Okay, we have 29 stars here, and we're going to do our focus scan right now. There we go. And you'll see the stars come into focus and go out of focus. It's building a curve. In fact, we can leave that curve up to show you what that does, how it works.
NBC 305, that is the debate we're experiencing. If they're physically associated, a true binary, yes, they would be orbiting each other. If they're just a line of sight thing, you know, two stars appearing to be close together just because they're along the same line of sight, then it's not a true binary.
You know what? I know. I just realized that. I know where that 5,000 astronomical unit study came from. James Kaler, K-A-L-E-R. James Kaler talked about it. That's where it came from. I just remembered that. It was a paper that James wrote, and that's the one I read. So it's okay to be wrong. Okay, let's focus now.
I thought I was wrong once, but I was mistaken.
Ooh. Hedrick says, Mark, could you please talk about well-known recurring astronomical events, 100-year events, 1,000-year events, 10-year events, sort of thing? Okay. And Daryl, of course, fill in where he'd like to as well. And that first, let's start with the sun. The sun has 11-year cycles, right? And those cycles, that cycle is seen most often in the sunspot count. The sunspots on the sun, which are geomagnetic or heliocentric heliomagnetic storms on the sun. Those storms on the sun are reach a peak every 11 years. So we have a solar cycle of 11 years. Well, of course, we have the orbital cycles, like, the Earth goes around the sun in 1 year. Pluto every 200 and some odd, I forget the actual number, 272, something, I forget, 252, I forget. But, so we have the cycles of that. We have the cycles of comets. Certain comets coming back, recurring, and recur. Those are called periodic comets, okay? Some comets are in hyperbolic orbits. They come through once and then they leave and they're gone. Thank you, Bonnie. So clearly, there's a lot of these cycles. Now, in terms of meteor showers, every year we have the Leonids, the Orionids, the Geminids, the Aquarids, etc., etc. And so that's what happens. And cosmic rays adding to the sunspot thing. He says changes in the sun's magnetic field affect the amount of activity on the solar surface. It's actually, it's not that the sun's magnetic field is changing. What's happened is the sun is a big rotating beast. And so what happens is that the magnetic field lines of the sun are getting pulled and moved and maneuvered by the hot plasma, which is charged. And that hot charge will sometimes drag the lines of magnetic force out. And it drags them sometimes so far that they reach the breaking point and they pop effectively. Think of it that way. And that's just what it happens, okay? And this causes the magnetic lines to basically disassemble and reassemble. And every 11 years this happens. So that's kind of cool. Okay. Right now that we're focused, let's go back in here and drop ourselves down. Alright. Now, I know it doesn't look really good right now, but just give it a second. As we drop the gain, look at that, look at that. Now, how about that? Huh? That's a beautiful, beautiful visual double star, known as Albireo.
Mark, would you like to show the veil composite that Izabela did?
Did she already put it together?
Yeah.
Excellent.
Let me see if I can get it over to you.
Just like last time, Izabela did it. She actually made a composite for us from our live data. So that's how fast things work. 248. That sounds more like it. Okay, so let's just check this out.
Okay, I sent it to your chat.
Yeah, I got it already.
There are other things that happen cyclically.
Cyclical events.
One that always struck me, there are planetary resonances that patterns tend to repeat over time, or their orbital periods are related to each other. One such is a resonance pattern between Earth and Venus. I was looking it up when Izabela sent me that. I'll post a link to it in the chat. That Earth and Venus have a resonance pattern. It's not every 5 years. They do a dance together in space over time. There's a neat diagram of this. We got too much going on here.
Well, and on top of that, I'm actually showing the composite right now that Izabela did. So it's going every which way. But yeah, here it is. You guys can see that, right? I'm hoping you guys can see that.
The end effect of what we see between Venus and the Earth is Venus tends to repeat where and how it appears in the sky every 5 years or 8 years or something like that. Okay, I don't see what you're showing.
That's because it was on the stream.
Yeah.
It's all right.
Yes.
Okay. Hey there, Paul Atreides. How you doing? Hi. Hey, no worries. Do you like Albireo? Let me zoom in a little more on Albireo here. Let me actually zoom in. Okay, let's do this. Wow. See the different colors? This is a K giant, and this is a normal hydrogen fusing B8 star. I think this is a K3, that is to say Roman numeral 3, so it's a giant star, but not a super giant. Aw, too bad. Guy got hidden from the channel forever. Alright, great. Thank you, Robin, for letting me know you could see Izabela's composite. Excellent.
You seem so nice.
Yeah, I know. Alright, guys, well, there you go. That's the eye of Cygnus the Swan. Right. And we had we turned down the gain to 0 for that. Okay, so if we want to go back up to start to see things, you'll notice how many more stars appear when we do that. Alright, and you'll see that, of course, by that point, when I go up to 350, the K giant pretty much overwhelms the B8 star over here, so in Albireo. So that's the way that works. Isn't that cool, though? Just wanted you to see that. Let's get rid of that. Okay, now...
You know, while we're at Albireo, we are so darn close, and we're taking good by looks at things tonight. You're very close to the dumbbell.
I am. Alright, let me just do one thing here. I'm going to move the telescope south a little bit. Alright, and then move us west a little bit. I mean east, the other west. Alright. There we go.
NPC 305. That is an exoplanet. I don't think we'd be able to see that.
Oh, we certainly can't see exoplanets.
Can or can't?
Cannot. Yeah,
But,
we cannot see those. Izabela answered that as well correctly. NBC. You have to, it's interesting. We're so used to seeing things like this in an instant. To actually see the exoplanets, it takes actually weeks of what's called reducing data in order to see these things. So it's not easy to capture, but once captured and confirmed, it's very cool. All right, now that's Albireo right there, and what I'm going to do is grab it, and then I'm going to synchronize on that, so this should go up there. Good, so we have now synchronized our coordinate systems. Okay, and since we're very close to this guy right here, let's go check out another beautiful planetary nebula. Off we go. Yep. And there it is. Dead center. I like it. Not bad. Alright, let's keep going here. Alright. This is the Dumbbell Nebula. It's the remnant again of a star that didn't go supernova, but it did what stars that are smaller in mass do. It actually expanded and puffed off several shells of material over its lifespan. Actually, once it stopped having enough hydrogen to fuse into helium, it began to burn other things, and it started to puff up into a red giant. It got so large that those outer shells just kind of sloughed off and became non-bound by gravity of the star because they were being pushed out. Very cool. I want to say hello to Charles Crito. How are you? It's Diamond Elite here. That was my nickname that Charles gave me when we were speaking at Exeter at a conference. Diamond Elite. It had to do with the hotel parking was for Diamond Elite only, and I said, we're Diamond Elite. And it was very funny. You had to be there. Dean Bostador, how are you? Now you want to see pretty, let's actually take a picture of it. This doesn't need a lot of time. We're going to only do 25 seconds on this because it's going to give us all we need to see. So we're going to come out of night vision mode and go into stack mode, clearing whatever else we may need to. We don't need to, so we're good.
So what we just saw was just a night vision look at the dumbbell.
That's correct.
Oh, well, just wait a second, folks.
And the wait is over. I've talked about a lot. We can actually let it process so you can see this is kind of what it looks like. This is way too much exposure for this because it's so bright, but we can actually do this. All right, let me take this down a little bit and kick the brightness down just so you can see. And this is even too big. Holy cow. I'm going to redo this. I'm going to do this as a 15-second exposure. Okay, and we'll clear it. Oh, I'm also at 350. I should have realized the gain should have been a little less because this doesn't need that much gain. But we'll see. You'll see. There you go. Now, this is the Dumbbell Nebula, and if we bring in all the details that are all around the outside of it, right, you can see now, okay, as we come in here, you'll see there's a lot of material out here. Look at this extra shells out here, all this. Now let's zoom in a little bit because I want to show you something. This is a lot of people's favorite dumbbell. It's everybody's favorite dumbbell. It's the only dumbbell. This is a lot of people's favorite planetary nebula.
You can see why they call it the apple core.
Yeah.
I'm always intrigued by that faint line. It's sort of a double teardrop shape, like a human eye.
This guy?
No, out at lower left and upper right, especially at the lower left.
Oh, this here?
That one very distinct green line there.
This one right here.
Yes.
Yeah. And it's also distinct on this side. Probably part of the same shell event. You know? These are probably the poles of the star here, and this is probably the equator of the star. Actually, the equator of the star is like right here, I believe. And so the entire nebula, the entire thing may have been doing this. It might have been precessing as it was generating these shells, and that precession could have been the same kind of precession like Earth is going through precession every 26,000 years. You know, so the same thing could be happening here potentially with stars. Let me do this. Okay, that's really bright. I'm going to drop this down to 100. I'm going to clear this and do a 15-second shot at 100. Okay, so we'll do that now. Alright, so Cosmic Ray says, is a planet bright? Is an exoplanet bright? Well, an exoplanet could be bright, but it may not be nearly as bright as the star for sure, and it's really, really hard.
As he said, they're mostly discovered. We only see them because they transit the star
Yeah,
in orbit. So you just see a little dip in the light curve.
that's right. Now this is
I mentioned at one point, I forget, it was one of the first exoplanets found, and I forget if it was Omaha or what was the other early one that they actually got a direct view of it.
that was the one of the Henry Draper guys, HD. I forget the name, and that was the Gemini telescope that actually got that. It actually saw several planets in direct light by occulting the star's disk, and you can actually see them going around it. And
Didn't they see one orbiting Omaha also?
oh yeah, yep, you're right about that one. That one took 10 years to flesh out and to actually see it going around Fomalhaut, but it was. Yep. Hey there, Bullwinkle. This is what I want you to see. This is the. It's a little dim, but that's because of what I'm doing. But I want to show you. If I brighten it up a little, maybe it'll be okay. Okay, there we go. So here's the Dumbbell Nebula as we've seen it before, and that star right in the middle is called a white dwarf. That white dwarf is really, really hot. It's 45,000 Kelvin at least, and what's happening is that star is so hot that it's ionizing this gas cloud all around the remains of this star. Right, we see this red, that's possibly hydrogen gas, maybe some neon that's being ionized in there, all over here, and it's that tiny little star, thousands of light years away, is the size of the planet Earth. Okay, but it's the size of the planet Earth, and it's so bright you can still see it from here. That's pretty big. That's pretty bright, isn't it? And that's how this works. But that's it's cooling, and the surface of the white dwarf is composed of carbon and oxygen atoms primarily, and there's no more fusion going on. It's literally called a degenerate matter star, right? And the only thing that's happening is it's got a lot of pressure to collapse, but because of something called electron degeneracy that happens in white dwarfs, the electrons are all shoved together so tightly that they're pushing back, and they're preventing the star from collapsing anymore. Okay? Now, if you were to add mass to that white dwarf, and it exceeds a certain mass called the Chandrasekhar limit, then that's when you might get the star trying to collapse more, but it can't, so runaway fusion begins in the surface, and the star will obliterate itself in something called a type 1a supernova. And that 1 is a Roman numeral 1. So that's something that's interesting, because these type 1a supernovae, if they occur, they are generally occurring in a way that happens the same way every time. So if they happen in a distant galaxy, if they happen here in our galaxy, we can figure out the distance to them because we know how bright they get. And so we can actually calculate distances using they're what's called a distance candle.
Mark, JSCO has an interesting question for you. I'm not sure I get it.
All right, JSCO, how you doing? I see an X in many planetary nebula. Any thoughts on that? I see the X he's talking about, seeing this and that. I think that has to do with the way the matter was sloughed off of the star. It's not... you don't see an X in the Helix Nebula, for instance. But you see it in this one, possibly because of the way this one did what it did. As I said, I think it might have done this, might have been turning like this while it was rotating. It was also pirouetting like this, like a spinning top. And stars will do that too, especially if they've suffered some kind of trauma, differential mass loss like this maybe. So it's possible that it was doing this precession. And if it did that, that could be responsible for different concentrations of material at different places in its overall appearance. So I hope that was helpful. So yeah, so anyway, so there's the dumbbell, and I think it's pretty beautiful. We've done 21 stacked. I think that's pretty good. And we'll name it up here. We'll call it the Messier 27 Dumbbell. And it's with 2 B's, by the way. Dumbbell. Okay, Nebula. And it's going to be a PN for Planetary Nebula. Alright. And we'll save it. It'll be up there for all to see. Just look at the colors of the stars around here. I have a big giant poster of the dumbbell that I got as a kid, and I just couldn't believe how beautiful that nebula was. I just couldn't believe it. And that was taken with inferior equipment back then.
Oh yeah.
Yeah.
I've mentioned Timothy Ferris's book Galaxies before.
Oh yeah. Yeah.
That was a landmark book back in the day.
It was.
It's been, imaging technology has so far outshone what was available back when that book was published.
I agree. But it was beautiful.
Yes.
Okay, we're going to go back up to 350 now. Alright. And go to 1 second. And into our night vision mode. There we go. And dim it out, or I should say zoom out. Okay. So here we are, we're out here, and now we're going to go back into our amazing, wonderful, connected planetarium. And now I'd like to take us to another object which is very characteristic of this region, and it is called the Crescent Nebula. So this is beautiful, and we're just going to zip right to it now. The Crescent Nebula is a location where there was a star that's gone mad, and that's the only way I can put it. The star has gone mad, and it literally started life as a big massive star, perhaps 20, 30 times the mass of our sun, and partway through its life, which was destined to be, a star that burns hydrogen into helium within just a few million years. It uses up the hydrogen, and then expand to a red giant after it starts burning and fusing other elements, and then blowing up in a supernova. But these mad stars, these absolute lunatics, what they do is they blow off most of their outer atmosphere partway through their lives. This star has done that. This right here, you see, this is the Crescent Nebula. That is the star. That's the madman. This guy right here. This star is responsible for this. And what's happened is it's kicked this material off, and it's done it by a series of complex events that occurred in the star that we actually don't quite understand. We know there's many types of these stars, and that name is a Wolf-Rayet star. Okay, hello there, Desert Dweller. And I'll put that name in right here for you. This is the Crescent Nebula. Wolf-Rayet star Nebula. Okay. So that is what this is. Right? And now let's actually move a little bit westward, pull it in, get it in here. Okay. Alright. Now we'll let our star lock system, our guider, get locked on. Up there. We'll see numbers show up here. Starts with zeros, initialization, there we go. And we're now guiding. And we will let that stabilize for a few cycles. and then we'll do a 35-second exposure of this guy. And I think, all right, we're stable now, so here we go. And there we go. So into our live stack, and before that we'll make sure we clear it, which is already cleared. All right, so this is the Crescent. I will remove that so you can actually see that come in. So the Wolf-Rayet stars are the super enigmatic stars of the universe. They are so hot, and for some reason when they blow off their outer layers, the middle, the core, the leftover core in the middle is still fusing other elements and still acting like a star does. Okay? This is a nova. No, it's not. Let me just... There we go. Okay. Just adjust colors. There we go. So, this star is still fusing here. It's still doing nuclear fusion. But it's still very massive. It's a massive core, and eventually it's going to just go boom! And it's going to... That explosive residue is going to overtake this nebula here, and who knows what that's going to look like. When they combine, when that overtakes this stuff, it's going to collide, it's going to heat it up to millions of degrees over what it is now, and we might see a spectacular nebula here. I would just love to see other places in the universe where a Wolf-Rayet star has gone supernova after it's done its business here of doing this expelling of its outer envelope.
Robin Curtis has a question, Mark.
Oh, I don't care about Rob. No, I'm just kidding. Robin is also known as Database Girl. Yes, Robin, what is the question? What does that mean? There are many types of WR stars? Yes, as a matter of fact, Wolf-Rayet stars have an extremely complex history, and there's many different kinds of them, but they're all Wolf-Rayet stars. They all do this thing here, like this. They blow off their layers. You know, when we look at this star, clearly this was its outer, its envelope. This was part of the star here, but eventually got blown off. And when it got blown off the star, it expanded outward and created this nebula. And that's what we're going to see, you know, moving forward. You know, and that's something that's, you know, it's moving outward as well. It's still moving outward, but that star in the center is the cause of it all, and will eventually go supernova, and when it does, it's going to be spectacular. Not nearly as spectacular as Betelgeuse, but it will be a very, very bright star. Yep.
There's one type of Wolf-Rayet star they even think is associated with planetary nebulas now.
That's true.
I don't know the details of it.
If you look at these objects, right, you would be forgiven for thinking this is a planetary nebula. Now, part of the problem is when you see a planetary nebula like the Helix, like the Dumbbell, okay, like the Blue Snowball, like the many others that we've seen, like the Ring Nebula, we know that in the center of those is a white dwarf. These differ because in the center of this nebula is a star that's still doing fusion. It's not a white dwarf. It's a very, very massive star still doing fusion with the hot central region that's left behind from this expulsion of the envelope. So that makes a difference. But differentiating can be tricky sometimes. So you might have these hybrid systems where you might actually get a star that's fusing and looks like a white dwarf, but it's not a white dwarf, or is a white dwarf, and it could be right in the middle. So it's interesting, the history of these objects. The guiding has been just great tonight, as you can see. This is just spectacular. We're getting some beautiful imagery here. Let me see if I can bring out a little bit more of the nebulous detail in this region. I'm sure I can.
There is a spaghetti nebula, is there not, Mark?
Yes, there is, and I want to do that again.
Okay.
Yeah. I don't know that we can see it now. I think that's in Auriga. No?
in a hamburger galaxy. Izabela's right. That's in Leo.
Yep, that's right.
Part of the Leo triplet, if I remember correctly.
Are we gonna do a food Messier marathon?
NGC asked about it.
Yeah. NPC.
NPC, sorry.
Yeah. Greg, I'm not sure what you mean. Does everything that has energy conscience? What does that mean? Maybe there's a typo there. Judy McClellan, how you doing? So good to see you.
I got my smileys back.
All right. Look at the clouds of red diffuse hydrogen gas being ionized out here by other stars. Isn't that pretty? You can see it much more clearly now with the crescent. Let's zoom in and check this out in detail.
Greg says yes, alive, meaning everything that has energy conscience.
Oh, okay. If I was an expert on life, I could answer that. But there have been people through the years that said the Earth is alive. There's a Gaia hypothesis and so forth. And I can't say it's not, because there are animals that have other animals living on them. So could it be that maybe we're an animal living on the Earth, and the Earth itself is alive, and we're like mites on the Earth? It could be. Could be. I don't know, Daryl. This looks like, I don't know, so much better detail these days we're getting out of the system. We've never seen some of these details in the past. We saw the completion of this right here, but look at the details here. Look at this nebula sticking out here, all these little parts. I've never seen those before.
Absolutely. Can we zoom in on that upper left part?
Of course we can. We're gonna. Okay. This is really, really red, and that's probably because of the hydrogen gas that's colliding with it up there, colliding with the interstellar medium.
Fascinating.
It is gorgeous. Look at that. I mean, little things too, like look at this little line of nebulous detail right here. What made that? And why is that like that? What happened there? We don't know. There's another one here, faint, but it's there. Look at this line of green around the outside. Is that doubly ionized oxygen amid hydrogen? Right? Very possibly. You know? Just incredible. There's so much detail yet to be seen in here and yet to be had.
Let's go.
Oh yeah. Yeah, it's beautiful. Let me just label it now, Crescent Nebula. And I'm going to put in WR for WR starts Wolf Rayet. Again, let's not forget what it is. Hey Alanis, what's up? Ryan DeBoer, how you doing? Man. Good to see you guys. Thanks for dropping by. Hang out with us. We enjoy your company.
Somebody asked about Betelgeuse.
Oh yeah, when will Betelgeuse be up? That's right.
Uh,
It's up now.
Betelgeuse is up now, but it's very low on
Yeah.
the eastern horizon. It's not visible to the telescope yet.
Yeah. And it would look like a bright red component of Albireo. You know, very, very bright. It looked like Antares might have.
NPC, you asked about the planets. Saturn is up, but it's going away quickly. It's setting at 10 p.m. or so. Jupiter is big and bright in the southern sky right now. And Mars is low in the northeast right now. Mars is also very bright. This telescope is not optimized for looking at planets. We looked at Jupiter the last stream and could barely really make it out.
Oh,
Had a little detail.
we could see the two main bands, but you know what? The next telescope is going to be designed to look, and we're talking about changing the camera on this one, so that we'll have a camera that has effectively smaller pixels, so we can zoom in more and get some gorgeous shots. So we're talking about that too. And then the new telescope that we get is going to have the same camera too as well, with the smaller pixels.
Izabela wondered about Mars. Mars is getting relatively big and very bright in the horns of Taurus the Bull now.
It's still low for us.
Yeah, it's still low. And one thing about Mars never gets very big from our point of view. It's presently about 15 arc seconds across. And when it's in opposition in December, it's only going to be about 17 or 17 and a half arc seconds across, which is tiny in the field of view of this telescope.
Yeah.
If you got the focal length, people are already getting great pictures of it, though. The North Polar hood is well visible. It's a big blue cloud over the North Pole of Mars, and the surface features are visible, but it's just not this telescope's bailiwick is to get really good looks at planets.
Yeah, we get really good looks at things like this. This is our forte. I mean, look at that. That's something you barely see in the telescope, and we're catching lots and lots of detail of it.
Yeah.
David Schmidt, how are you?
This is more of a deep sky telescope.
Yes. David Schmidt says, how did that nebula know I was going to pop in today? I don't know. I don't know, but that's funny.
If you've been here for a while, you might remember about 2 years ago we were looking at Mars, and we were
right.
barely able, that was near opposition about 25 months ago, and we could barely pick out a little detail on the planet, but we were having to zoom way in on it.
Right.
And it was very difficult to see some of the details.
Okay, we're saving this after 22, save exactly as seen. And we will get rid of the stack. Bring back telescope, just move that over so I can see the telescope. There we go. Yep. And we'll go to our 1 second and do the night vision. There it is. It's a beautiful night out there, as you guys can see. So it's very hard for me to want to go to sleep when this is the case. So I'm not gonna yet. Alright, so we did the Crescent Nebula, which is down here. Next, roaming through Cygnus will take us to Sadr, or Sadr, depending on how you want to pronounce it. And we'll just go to Sadr directly. Alright, and then from Sadr we will go to the other objects we'd like to see. Look at those star colors. There's Sadr. And right here is the Gamma Cygni Nebula. Sadr, of course, is Gamma Cygni. Alright.
Yeah, Mars is up now, but it's just it's very small. I don't think it would show much in the telescope.
Yeah.
I'm consulting a star chart.
Okay. Okay. I'm going to move us a little bit to the east.
Once Taurus is up higher, maybe if and when we can look at the Pleiades and the California Nebula, stuff like that,
Yeah.
Mars might, be worth a passing look, but we won't see much. It'll just be bright and reddish.
Spoil sport. How do you know? We might be able to see something amazing.
well, we might, but
I mean, don't hold your breath. I know.
When we see, Mars is only actually twice the diameter of the Moon. The Moon is 2,000 miles across, and Mars is 4,000 miles across, or about half the diameter of Earth, and it's still far away. It's you're probably talking on the order of 40 or 50 million miles away right now, and so it's just not very big in the view of the camera or the telescope.
Nope, it's not. Okay. Alrighty. This is the Gamma Cygni Nebula. Ladies and gentlemen, boys and girls. And for your viewing pleasure, I am going to take an image of it that will knock your socks off. Because it's going to show you, this one image is going to show you what is mostly populating the universe. And it lies in this region you can't see here, where it looks like a void in the stars. So let's do we'll do 30 seconds on this one. Okay, and we're off and running. Go into the live stack. And that's the previous one we saw. That's the beautiful Crescent Nebula. And we'll clear it now. Alright, this will be the Gamma Cygni Nebula. Gamma Cygni is the star Sadr. What's that?
Having changed with data.
Oh. Okay. Let's check it out. Wow, look at that. Okay. Now, this is really cool because you actually can see these dark patches very clearly, like this one here. Alright. This is only one image. Now we're going to have two stacked. You'll see the noise disappear. Look, it gets darker. The contrast is better. And as this happens, you'll see something interesting. You're going to notice that this dark line is not a void in the stars, but it's actually a dark band of dust overlying a nebula behind it. In fact, in some places, the nebula is showing through. Right? Like there, and over there, and here, and here. So this is overlaying it on top, and the nebula is, behind it like this. And this dark thing is up in front of it. Interesting. Izabela asks, is the Gamma Cygni Nebula also an exploded supernova? Not directly, but what it is the stuff that's here is the result of supernovae that went off elsewhere, right, over the many billions of years and accumulated in the galaxy. So we're seeing hydrogen gas, some of it from the very, very beginning of the universe, some of it left over from stars' envelopes after they were finished with it and went supernova. The dark dust, on the other hand, this was made by supernovae elsewhere in the galaxy, and over time was distributed throughout the galaxy. Everything feels gravity, so everything is being tugged on, no matter where it is. Everything's being tugged on. Yep. So let's do this. Let's see if we can. Let's see if we can separate that dark patch in the middle a little bit more. Maybe this will do it. And then we'll zoom in on it and show you. Alright, that looks like that'll work. So let's zoom in now. We have 5 stacked. We should be able to do this. Yeah, we have a little noise. You can see some noise, but look at these dark lines. These dark patches. This is where there's molecular carbon, silicate compounds, silicon molecules, silicon atoms, and silicon little spindle dust, like carbon atoms that are combined and coalesced into long spindles, a few microns across in size. And those pieces of dust will accumulate ice on them. Ices from water, carbon dioxide, methane, ammonia ices, formaldehyde, cyanogen, cyanide. And so those ices become a slurry of planet-making materials later on once they're melted off, once a new star forms. This is something that is amazing that happens in the universe. You see this dark ribbon coming through here, and it just keeps going. Okay, here you see it separate. You see the stuff behind it, the bright nebula behind it, and then it's overlying the top here. It's not a void. You can see how it thins out, and oh, it's just beautiful. Look at all the detail in this one little section right there near Sadr itself. See that? That halo is the artifact of the system. So what do you think of this, guys? Isn't this something? Oh yeah.
Star factories, I assume.
Yeah. Dark nebulae are star factories, as well as these clouds that are lighting up are part of a vast stellar nursery system that is these stellar nurseries are actually part and parcel to what makes up the universe and all the stars. And this used to be a dark, unseen gas and dust. But then once a star is formed in here and ionized it, well, then it became visible. But that's what's lying out there, Izabela says, is this new music for STLS? It sounds a bit unusual. Yeah, this is a whole new playlist. Some of the songs sound like they ought to, and a couple of them are kind of weird, kind of cool. So there we go.
Mark, could you excuse me a moment?
Yeah.
Okay, I need to put this tea down.
All right.
Be right back.
No problem. Hey, David Jones, how you doing? Great to see you. Thank you for coming, man. This is a beautiful nebula. You know what I find interesting, guys? We're doing this live. This is not a photo that was taken the other day or an hour ago. This is done minutes ago. We're doing it. It's adding to it now. We're seeing it adding. We're taking new exposures and stacking them on top of each other, one on top of the other. And that helps things that are dark and faint, like these subtle details over here, to come bursting forth and rise to the top of the data pile. And the noise that you'd see gets relegated to second fiddle. Okay, so as I zoom in, you'll see what I mean. Okay, you can still see there's some noise around here, right? The more images we take, the more that noise will go away. The first image that was taken, this was all noise, but then stacking up this black material says, no, I'm an actual piece of data, and I'm very subtle, so I want to make sure that I'm there. So this gets added onto itself over and over and over again. So far, 14 times. As you can see down here, this is the... Oh, you can't see that, can you? You can't see that, I'm sorry. Let me see if I can change that. Let me come out of that for a second. There you go. So 15 times by now. So 15 times you can see this was added and stacked on top of itself. So this noise gets less and less and less. Look at these three little stars. What if you lived on that star right there? What if you had planets around that star? And there was life. You'd be looking at us possibly saying, I wonder if there's life around that star. Isn't that interesting? I've told you this before, the universe is my cathedral. This is the stuff that just keeps me moving through life, is this beautiful universe. Hello, Cindy Murphy. It's so nice to see you. How cool. I'm glad you're here. And poor Robin. She's doing our database. And every time we do this and we start doing tons of these objects, oh, poor Robin. She has to go in now. Go ahead and put them in the database. Papa Kembu, back from Bali, Indonesia. How are you? Thank you for coming out and checking us out. Okay, we've got 18 stacked here. We'll go to 20. JSCO asked a question that I was talking about just today, actually. Where the Earth is located in space, is it a relatively dust-free area? And the answer is, I don't know. I'm actually not sure, only because I'm ignorant on it, actually. I don't know if there's been any studies of dust clouds to see if we're actually in them. But think about this. If you're inside the dust cloud and it's uniform all around you, as it likely would be, because the variations that we see in these clouds are light years in length, okay? But if you're in this area of a cloud where there's some dust in the area, how would you know? By looking out from inside of it, how would you know? You wouldn't. The only way you'd know is if you could see a spectrum behind or in part of everything you're looking at, because the dust would contaminate the spectrum of any star you look at or anything else you look at. That dust should show up in the spectrum. I don't know if that's been done.
There has been, I've seen some recent stuff. They think there may be some nearby nebulosity.
Yeah, and the thing is, if you notice the way you're saying it, they think there is, because it's like you're inside the forest trying to decide what the forest looks like.
Right.
We can't see it from the outside, so we don't know. You know?
I would have to see if I could find. Give you a moment. Hold on.
Okay. So JSCO, that's a good question. I tend to think that we're probably in a localized dust cloud of some kind. So, I don't know. Hedrick, you heading out? He says, back in time to say thanks for the great time. Hey, J. Rich. Oh no, is that the hostile thumbs up icon? No hostility. Give us a thumbs up, Jay. Hang out with us. Alright, cool, Hedrick. I thought you were heading out. Glad you're sticking around. See how much detail is in this nebula? This nebula, I actually took a mosaic of this some weeks back. Astonishing how much detail there is. And I went all the way up and all the way down. I made a big long mosaic. And I worked on it privately. I did it on my own. And it was just something, you know. Yeah, we're not done yet, Hedrick. We got a few things to look at yet. Alright, so this is beautiful. So we've stacked 24 of these. We're going to go to 25 and then we're going to pause it. But this is beautiful. I actually, to be fair, guys, I was a little bored of this nebula. Because I said, well, Sadr's in here, pain in the butt. But then I thought, look at the detail. Look at all the complex black, dark dust nebulas. Okay, we're done here. I'm going to pause it. And I'm going to change this to Gamma Cygni up here.
A quick look says nebulosity near the Pleiades or the Helix Nebula, which are hundreds of light years away. I may have phrased the question wrong in search terms in Google, but I know I've seen 2 or 3 articles fairly recently that were talking specifically about an area of nebulosity that was actually in our neighborhood.
Yeah. Well, considering that the Pleiades is like 400 light years away, and those stars are going through a dust cloud, considering that the Helix has dust near it, and it's only, 600 light years away. So the idea is that we might be traveling through a similar dust cloud, but inside the dust cloud, we can't see it. We can only see it against the backdrop of something else that's traveling through it with us. So, very cool. Okay. We're done with this guy. You still with us, Daryl?
Yes, sorry.
Oh, okay. Sorry, I thought your machine might have crashed on you, because...
Oh, no.
Okay. Alright, so we did this. Gamma Cygni Nebula will be up there momentarily. We'll clear that, get rid of the stack, jump back into our amazing night vision scope system. Here we go.
Can't talk, eating.
Yeah, right.
Homer Simpson.
Can't talk, eating. Hey, Homer, look, a peanut. All right. Okay, here we go. Oh, where to next, Mom? I don't know. Let's go have some fun. All right.
Sorry, I was eating a cookie.
Oh, I'm not mad at you. No problem. We're fine. All right, let's go see. Oh, you know what? We missed another beautiful object here in the Milky Way. This guy right here. I believe this is the Tulip Nebula down here, correct? I think it is, and I think it's the Tulip, and I don't think that all right, we can just go here. We'll find it. Off we go. Telescope will move a little bit. Zinga. Alright, and right there in the middle of our view is that exact location we want to look at. So we'll just let that stabilize. There we go, move it up a little. We'll let that stabilize and do a 30-second shot on this. While we're waiting, what I'll do is I'll come back into this, and I'm going to bring in some catalogs of some of the other objects we want to see. Okay. And then we get the Cygnus star cloud right here. And that right there is where we are. It's otherwise known as the Tulip Nebula. And that's where we are. So, We have a 30-second shot. It's underway. Let's get rid of our night vision system and jump into our stack system. Alright.
Well, darn it, I'm not finding anything. Sorry.
Alright, no worries.
There were a couple of articles that they talked specifically about a nearby cloud of nebulosity in our stellar neighborhood.
Yeah.
Oh, well.
Look at this. This is really pretty. This is going to develop into a very beautiful nebula in just a few minutes. And you see this dark nebula here? This is a dark cloud again. It's not a void. Yeah. Bapak Embu, thank you for contributing to our chat, but your translator is not making it something we can understand. I'm sorry, my friend. You were
Robin has a question.
You were accidentally timed out, Bapak. It wasn't. It was an accident. Sorry. Robin Curtis, if we were searching a catalog for items, we could see how big should the how big would the objects we can see be? Okay. Depends how close we are to them. When we look at supernovae, for instance, I may have misunderstood your question, but I'll say it anyway. When we look at supernovae in Messier 33 in Triangulum, they're tiny, tiny, tiny little, just a few pixels across. We look at supernova here, and it spans multiple degrees. So I may not understand your question. Meanwhile, let me just say hello to John G. How you doing? Look at this nebula. Isn't that pretty? This is music for stacking a nebula by. I like that. Okay. Let's move in closer now. We'll still have some noise, but you can start to see some beautiful shapes taking place inside here. This dark nebula here is encroaching in and sticking out into this stellar nursery region of the nebula. And look at this beautiful blue star and this beautiful orange star that dominate this nebula. Aren't those beautiful? When you look at this with a regular telescope with your eye, you can see these two stars and a hint of nebulous detail. Dallas Herrera, how you doing? How is it that we see but can't? That sounds philosophical, actually. Hello there, Claudio Ramos. Nice to see you again from Chile. It's good to have you back, my friend. Glad you joined us. Huh?
Cosmic Ray may have found it. He talked about the local interstellar cloud.
Okay.
Which I'm looking at now. Yeah, I think that's what I saw. They have an interesting couple of images of it.
Yeah. Yeah, that C. Ramos there, that's Claudio Ramos from Chile, who's joining us. Thanks for stopping in with us, Claudio.
Local interstellar cloud, also known as the local fluff, is the interstellar cloud roughly 30 light years across through which the solar system is moving. This feature overlaps a region around the sun referred to as the solar neighborhood. It is unknown whether the sun is embedded in the local interstellar cloud or is in the region where the cloud is interacting with the neighboring G cloud.
Mm-hmm. Oh, Robin, were you talking about the size on the image sensor? Because Cosmic Ray answered your question by saying the image sensor is 4 full moons across, so size must be compared to that. Is that what you're looking for? Sorry, I'm only doing 5 things at once, so sometimes I get sidetracked and don't fully get the meaning. Hello there, D. Smith.
Huh. That's actually interesting.
Yeah. Hendrick says, Marc or Daryl, is it true that photons can take 100 years to reach the sun's surface? Actually, when I was getting my degree in astronomy, one of my projects I had to do was actually build a star and do it in the computer and calculate how long it would take for a photon to go from the core of the star to the surface and get out. Some of my photons took 1 million years to get out. All right. Now I had a moderately massive star, but you know the photon is getting sidetracked every single step of the way. Every single step of the way. So it could be 100 years, it could be 1,000 years, and I think it depends on how energetic the photon is, and what particular energy path it's taken. Not all photons are the same. You know, you have photons, for instance, that are generated by when a hydrogen atom combines with another hydrogen atom or a neutron to form deuterium. Okay, well, you get a release of energy there, and when you release a neutrino, well, that just comes sailing right out. Okay, at the speed of light. So those just zip right out as if nothing's there. Okay. And so when you're talking about other particles, then like just standard photons like you're talking about, in one of my star models, like I said, it was like upwards of 1 million years. And I thought it was the wrong answer, actually. And so I kept trying to work it to see if I could get to a lower number. And I couldn't. So that was based on Eva Novotny's Stellar Atmospheres book and the formulae contained therein. So it was just crazy.
You might say that if a photon is released at the center of the sun, it takes so long to get out because there's so many more atoms in the way that constantly absorb and re-emit the photon.
Yep.
That it's like a piece of popcorn inside a great big bowl of popcorn. You know, while you're popping it, it's going to be stuck inside there for a long time.
Yeah.
Once it breaks through the surface of the sun, the photosphere, I guess.
Yep.
You know, then it only takes 8 minutes to get from the sun to here.
And it has to go through the corona too. And the corona is actually hotter than the sun. So hotter than the surface of the sun by a couple million degrees or so. So it's amazing. It'd be kind of an interesting YouTube video to do, the path of a lifetime of a photon coming from the sun. It's not over in 8 minutes. Yep.
Per Izabela's question, does gravitational time delay have something to do with this? Golly. Probably not much.
I'm not sure. Gravitational time delay?
Well, she's talking relativistic effects, I assume.
Oh.
I saw a presentation back in the late 90s. I attended an Astronomical League convention that was held here in Colorado.
Yeah.
And they had one speaker, and I can hardly do justice to what the guy said. But he said, in effect, that due to relativity, the sun is actually about 800 meters smaller in diameter than it would be without relativity. That is, the curvature of space-time, I guess, in the center of the sun is about 800 meters deep. I don't know if that makes sense or not.
I'm just getting a all sky shot here. There we go. Let me just show you the all sky right now, guys. So there's the view. There's the Milky Way. Okay, that obviously is Jupiter right there. And we have beautiful Milky Way, and we're hanging out. We're hanging out up in right around this region here. If I don't miss my guess, I'm trying to look and see. Right now we're up there.
Robin, as Ray alluded to, the image is about 2 degrees across by 1.5 degrees high.
Yep.
And there are 60 arc minutes in a degree and 60 arc seconds in a minute. And generally in this scope, we have looked at quite small objects. As a general thing, though, something 1 arc minute across is going to be very small on the screen, and depending on the object, probably not interesting to look at. Something with a little size helps, because again, this is a low power wide field telescope.
Yeah.
Looking at deep sky objects, which hopefully are going to have a little size to it. When we look at the moon, it's 30 arc minutes across, half a degree. And you might be surprised actually how large some deep sky objects are. We've looked at some planetary nebulas. The cat's eye comes to mind. I could be wrong about this, but it's actually on the small side as far as deep sky objects go. And
yeah.
It looks kind of neat, but it's not really particularly interesting looking as such things go, just because it's so small.
Yeah. But when you look at it with more focal length, wow.
Yes.
That's pretty amazing with more focal length. So this is
when you see images like from the Hubble or from the web nowadays, I suppose, those are very long focal length, narrow field instruments.
Yeah.
And when you see some of the pretty pictures from the Hubble, for instance, those are actually built up mosaics of many contiguous shots taken to build the image.
Yeah, like
that's the ones that's the ones where it looks like the bat plane or something. You know, there'll be jagged edges or a series of right angles to the image.
Yeah, like that's like what Izabela put together for the veil composite earlier from our images we had just finished taking.
Exactly.
Okay, we've got 26 frames here. We're going to go to 27 frames. That's this frame right here. Boom, turned over. We're going to pause it. And I've got Tulip Nebula up there. We're going to save it. Excuse me. And save exactly as seen. Then we'll remove this and go to the next object. Alright, and go into our night vision mode. There we are. Alright, we back out. There we are. Alright, so now let's continue going back up to up into the center of Cygnus and beyond.
one more you have to do at least.
This one here.
Yeah.
You got it. And we'll actually, we'll have the telescope just go to this location, not a particular object. We'll just have it go to this spot. That's all I care about. We'll just make it go there. Alright, so we're just going to tell it, I'm going to need to select, we'll say go there. Alright, and it will go. And you'll see it come in as these streaks of things that look like hair come in. Alright, and there we go. So, this is the North America Nebula here, and this is the Pelican Nebula here. And we're going to move a little to the east a little bit. Right. See, if I want to take a picture of just this, then I gotta exclude that. So I'm gonna leave that at the edge, and we'll do it like this. So we have most of this. This is called the Cygnus Wall. This is actually a buildup of gas and dust here. Uh-oh.
Uh-oh.
Okay, that's better. Alright, this is a buildup of gas and dust here. And so what we're gonna do is do a 35-second shot here. Alright. And we'll get out of night vision mode. We've been guiding, so I think we're good. And we'll go into our live stack and begin stacking imagery. That's the Tulip from last time. That is going to be up there. It's actually up there now already. So you can go look at it. Izabela has been amazing. She's been putting up all of the links to these for us. Alright, look at that. Amazing. This nebula is especially good to show you how the dark nebula sits in front of a brighter nebula. And I'll be right back to you in a second. This is called an emission nebula, and it has a dark nebula as well, but it's mostly the emission nebula. So that's what this is. North America Nebula. Hedrick, that's a heady question, asking if a galaxy could ever be surrounded by an extreme time shift, meaning a different time rate. Well,
yeah, we've talked about this before.
We have talked about it, and now
if you're in a different gravity well, time is different in another gravity well.
Yep.
It's all part of relativity.
Mm-hmm. Okay, we have the object. We know what it is. We'll take that out for now. Oh, look at this. Let's make some adjustments. Where's let's color correct our curves. Okay, and then we're gonna do another adjustment. Wow, look at that. Look at this. Look at how subtle all this detail is over here. Isn't this incredible?
Yep. Looks like Mexico's glad to see it as usual.
Look at this beautiful detail in here. See how it's like it's just being, it streaks like this. Now what causes that? It could be the motion of the clouds trailing behind as the main cloud is moving through the galaxy. You know, very interesting. And then more, look at this up here. Look at how amazing that is. Again, this is dark dust. that's made of carbon atoms and silicon atoms that have probably coalesced ices on their surfaces, as I said, formaldehyde, methanol, water, carbon dioxide ice, and other types of ices, cyanides, and other materials that become the veritable planetary panoply of materials used for the building of planets at some point. And then you've got these beautiful regions. Look at this. These stalks here, like that. Again, all related to the way a nebula forms and the way that the gases are ionized by the stars that are doing so. Now, in this case, the star that's doing the ionization is not even visible. It's in this cloud. It's behind this cloud. So this entire nebular region, all this, is being ionized by what's hiding inside the dark. Right? So if you look at this guy up here, this is the Pelican Nebula. This is the pelican's head right here. There's the bill. See, the eye would actually be here, not the star. Okay, but the pelican has this bright red area in it too, and it makes you think that it's being ionized from over here somewhere. Not necessarily. It could be getting ionized from way over here, but it's going through this material, and the ionization is actually showing up over here. That's very, very possible. You know, so there's a lot of complexity to where all this is coming from, and guess what? Nobody really knows fully. So that's possible that that's happening just because it is, and that's all we can say. Okay, this is really pretty.
Yeah. It's thought that I read Edwin Hubble thought that Deneb was illuminating the North American Pelican nebulas, and we've talked about this before, that nowadays they think there is one or more super bright stars behind that dark cloud between North America and Pelican nebulas, actually doing the illumination.
Some very hot stars.
It's not just lighting it up, it's very energetic stars, and as ever, you know, it's ionizing radiation which is causing the gas to glow. Emission nebulosity, in other words.
Yes.
It's not reflected light.
Mm-hmm. That's right. Gosh, this is something. So we've been taking a heck of a journey tonight, guys. We've been going all through Cygnus and looking at all the stuff left in Cygnus, the constellation that is going to quickly reach a location where it won't be as valuable to us because it'll be too low to the horizon. We won't be able to see as much in it. But if you notice where the telescope's pointing, you can see it's pointing way over that way. That's toward the northwest. It's looking out and back toward the northwest. So it's going that way. Okay, so that's pretty, you know, pretty cool. We have the room. Look at that. 12 stacked. Oh, that's just beautiful. As you guys know, my thing is the dark details. Look at this. Oh, stunning, gorgeous, dark nebula. Again, the seed of life in the universe springs from here. This is where it comes from. All from within these dark clouds. Just remember, every star is born in the dark. And so is life.
I don't remember if I posted this earlier. I'm going to post it again.
Okay.
This is relating to that question about the local interstellar cloud. This is a really cool illustration of it.
Okay.
posted in chat.
Yeah. John G says Pelican Nebula, 1,800 light years away. Thank you for that. Yep. Yeah. We're looking at the most amazing locations in the galaxy right now, primarily because we're close to them effectively. Look at how beautiful this is. The complexity in here. We can change the view here to actually be able to sort of make the area just a little bit more transparent so we can see what's really going on in there. That's called push processing. We're doing it right now. Okay, so now you can see and get a feel for how this stuff is overlaying a bright nebula behind it. Because you can see the bright nebula showing through in places. And there's a star in here somewhere, deep in this nebula, that is ionizing all of these clouds of gas and dust. Wow.
Hedrick, that may be above my pay grade. I would have to guess so, yes. As a general thing, look up space-time diagrams.
Oh, can you find time dilation from gravitational lensing?
Yeah.
Oh. Well, the way gravitational lensing works is that you have a large gravitational body sitting in front of a much more distant galaxy cluster, which is typical. So, in that case, any time dilation that occurs would only be due to the relativistic motion imparted by the galaxy in the foreground that's lensing what's behind it. And that number is directly related to the mass of the galaxy. So you could calculate what time dilation might be, all right, but it has to do with the motion, right? Time dilation, of course, occurs because of motion. And when we look at an object that's a galaxy, okay, being lensed, we have to consider that you need to consider the motion of the objects for that kind of thing to be of any value. So maybe high cosmological redshifted galaxies that are really far away, moving at very relatively significant speeds, a fraction of the speed of light, that would probably be something where that would be an interesting calculation to perform. Okay. Now, here's one for you. How long of time, Hedrick, this is a question for Hedrick, or anyone else, not you, Daryl. How long
Be that way.
Yeah, I will. How long does it take, or how much time would pass for a photon leaving the sun and getting to the Earth? Let's say it's at the surface of the sun and coming to the Earth. How much time does the photon experience going from the surface of the sun to the Earth? That's a question for you in chat.
Or for that matter, how much time does the photon experience when it's flying clean across the Milky Way galaxy?
Or
to the far side of the universe.
Okay, Cosmic Ray says 8 minutes. Hedrick says no time at all. John G says what? Robin Curtis says none. Okay, as Hedrick said, none initially. Depends on what you define surface of the Earth. Actually, John, no, it doesn't. What we're talking about is going from the sun. Give me an order of magnitude. It doesn't even have to be exact. From the photon's point of view, how long does it take to go from the surface of the sun, where it comes out of the surface of the sun and heads to the Earth? Okay. Jay Rich says infinite. Yeah. Okay, Dallas Herrera says I'd say in under 9 minutes. Okay, we're getting a lot of interesting answers. Izabela says instantaneously. But again, from the photon's point of view. All right. Bullwinkle says 8 minutes. And that is indeed how long it takes light to reach us from the sun. But from the photon's point of view, how long does it take for it to travel from the sun to the Earth? Remember, it's all reference frames. This is a relativity question. And while you're answering that and thinking about it, I saw a lot of answers so far. We'll just keep looking here. We've got 23 stack. Look at this.
Ray asked basically how thick those dark clouds are.
Good question, Ray. There's really not a whole lot of ways I can answer that because we don't really know how thick they are. We do know that you'd have to do a specific study to see how deep the clouds are. And to do that, you basically only have the light to look at. So you have to be able to get in there. And I think what you want to do is consider a telescope that could actually see into the clouds in order to gauge the depth, for instance. So in other words, if you saw a star just at the edge of visibility with the James Webb Space Telescope looking as far into a cloud as it could, you're seeing farther across the cloud than you are with, say, the Hubble. So we need to look deep inside the clouds to do that. And John G, yes, use infrared. We'd want to probably use infrared light because most of the stars we want to see are hidden inside there. We can't see them with visible light. So we have to do a different type of study. Infrared stars forming inside there would be one of those. Okay, anybody want to know the answer now? From a photon's point of view, how long would it take the photon to go from the sun to the Earth? How much time would pass for the photon? All right, I will give you the answer. I'm proud of some of you. You got the right answer. For those that said 8 minutes, I'm sorry. That's not the right answer. That's how long it is from our point of view. From the point of view of the photon, it's instantaneous. So when we say that the photon leaves the sun and takes, say, 1 million years to get to the surface and come to the Earth, to the photon, that's instantaneous.
Yep.
And
that 8 minutes from sun to Earth is instantaneous.
Yep.
And clean to the far side of the Milky Way is instantaneous.
And the universe, for that matter.
And to a galaxy on the other side of the universe is instantaneous.
You got it.
No time at all.
And now the reason... prove it, because Grace says, prove it! Actually, it doesn't take much to prove it. Because you just have to understand how things work at light speed. At light speed, for you, if you're in a ship traveling at light speed, there is no passage of time. Okay, the time has stopped for you. All right, so for you, you would just be starting out at your destination and getting to your destination, and be like in a split second. But there's someone watching you do it. They would see you. Let's say you went by the Earth, okay? You went by the Earth at light speed, and in your ship you're zipping by the Earth, and it goes by pretty quick. And to you, you're waving, hi, okay? Let's say you could do that. Well, inside your ship, you'd be waving, and in the middle of your wave, you've already gone from your origin place to your destination in that split second. But people on Earth watching you go by, waving, they're just going to see you frozen. Forever and ever and ever. They're going to see you in the middle of a wave saying, and that's what they'll see. It's called reference frames that we have to worry about here, and that is the reference frame analogy that I always talk about when we talk about relativity. Where's the viewer? Where is the particle that's receiving the effect? Right? Hey, Marvin. Nice to see you, man. See? So, I think that the universe being a amazingly crazy place to exist in is really, really amazing to consider some of these puzzles and conundrums. You know, Izabela says quantum entanglement's another fascinating theory. Actually, Einstein did call it spooky action at a distance, and there's a reason that he did, because if I took a piece of material from this object and split it off here, and took some of its atoms and took some of the atoms of it over here, and moved them 10,000 miles away, all right, or even say a few hundred feet away, and I changed what are called the spin characteristics of electrons in this material over here in this lab, I would not have to measure the ones over in this lab to know that the ones that were spin up over here means that the ones over here are spin down. Okay, the ones on the other laboratory would be spin down and these would be spin up, and I wouldn't have to measure that to know. They would just be the case. But if you measured them, okay, if you measured the particles here and you saw that they're spin down, you know that they're spin up. Change them to spin up, and those change to spin down. Now, those are atomic characteristics, particle characteristics. Let me ask you a question, okay? What do you think would cause something like that? Big question. It's a really big question. And that something is, of course, quantum entanglement. At some quantum level, those particles are still in communication instantaneously across great distance. Spooky action at a distance. So think about the next thing, and that is take it to the human level. I actually was talking to a group of 800 people at a conference, and I mentioned, when I first walked out, I said to them, before I get started, I want to ask you a question. How many of you have thought of a friend you haven't talked to in many, many years, and bam, that friend calls you on the phone? Every single hand went up. Every single hand. Not one person didn't put their hand up. Of 800 people, every hand went up. It was the silliest thing I ever saw. It's like 800 people all wanting to ask a question. Well, as it turns out, that, to me, is exactly what quantum entanglement is. We are quantumly entangled with people we know, people we share with, our relatives, our friends, other humans. We're quantumly entangled at a level in the brain that we don't yet understand. I call it the brainular level. I made up the word brainular. Okay, that is quantum entanglement at the macro level. And I think it stems from quantum entanglement at the atomic particle level. And that's a theory, but I believe it's true. So there.
I've mentioned before, high school sweetheart and I, one of us would think about the other one, and I think I'll give them a phone call. And we'd go and pick up the telephone, and there'd be no dial tone on the other end.
Because you're talking to someone already.
And finally it'd go hello, and they'd go hello.
Yep. And you know what? That just tells you that Daryl's hand would also have been up. Okay, so that's the spooky action at a distance at the human level. And this is all just science waiting to be discovered. I call it science undiscovered. And it will be something that we will, in maybe 50 years, 60 years, 100 years, just accept as fact and have a full understanding of. I believe that.
Izabela has a question of you.
What does Izabela want now? Marc, to my question above, can we experience glimpses of another universe because of quantum entanglement? Good question. I've had experiences that might border on parallel universe things, but I don't know if quantum entanglement was involved there. That's a good question. It'd just be speculative at this point, is.
Yeah, I think no. Another universe is another universe. It may exist, but from our point of view in our universe, it's inaccessible.
Well,
at this time, at least.
At least you'd like to think that, Daryl.
Yeah, well,
What if it's not? What if it is accessible? What if it's not inaccessible? What if there's bleed through because the theories about the universe, concurrent universes, is that they're concurrent shells that kind of bump into each other, push through each other all the time at every point. And so we as humans experience what that looks like when we see something that we call a ghost. Is it a ghost, or is it just bleed through from a parallel universe?
Yeah.
So it could be that. And there's no science around that because nobody wants to talk about ghosts as a scientific thing, right? Because that's just silly stuff, right? There's no such thing as ghosts. Well, there was no such thing as faster than the speed of sound travel either, wasn't there? So clearly, that's something we have to consider. All right, I'm going to stop this now because we are at 40. Oh, look how beautiful. Look at this. I just noticed this for the very first time. Look. Look at this beautiful little spindle of dark dust right there. Look at that. We've never been able to see that before. But with 40 stacked frames, wow. It's just beautiful. We're cruising through the North American Nebula now, guys. Look at this. When I zoom out, you'll see how it's pretty obvious how this black thing is an overlay over a lighter region behind it. You see it now?
Yeah.
Sticks out just like an overlay. And that's what we got here. Amazing.
As for Ray's question about, how dense are those clouds?
Yeah.
I would say, well, they're still a vacuum. They're a slightly less dense vacuum, but they're still a vacuum.
I think they're many light years thick, okay? But I think that it's not like they're dense like clouds on Earth. Clouds on Earth are probably like 10 to the 50th or so more dense than these clouds here. Here we're talking about maybe 30 atoms per cubic centimeter, okay? That's not a lot when you consider there's trillions per cubic centimeter, okay? in the air. So it's just that you're so far away from them that you don't even you'd pass right through them and not even know you did. Yep. Just like thin cloud, or just like air in our atmosphere.
We've talked about this. May have been more in the sense of bright nebulas instead of dark nebulas, but golly, if I were in the middle of that, how pretty would that be? And golly, if you were in the middle of it, you probably wouldn't see it at all.
You certainly would not see it.
It's because we're seeing it at a distance, and it tends to concentrate things.
Yeah.
If you were in the middle of that, you wouldn't know you were in anything at all.
That's right. I don't want a snapshot. Stop it. Cancel. Okay.
Yes, Ray, but can you reach out and touch it? It's so thin that you need light years of depth.
That's right.
For that to build up to where it looks significant.
That's right.
It's not like you could reach out and scoop up a handful of that. It would be pretty much nothing. A few atoms is all.
That's right. Again, imagine just you're only going to have like 30 atoms per cubic centimeter possibly, and that would be considered dense.
Yeah.
Now, if you're traveling in a ship that is near the speed of light, those 30 atoms could tear right through your ship. Okay, so you need a way to get them to not go through your ship. And there are theories about it. The LQBA drive is one with using the Froning variant of the LQBA drive. They actually have a way to shunt material over the top and bottom of the ship to keep it from striking the ship.
Yeah, well, you're getting into shields and screens and Bassard ramjets and all sorts of stuff.
Well, shields and screens anyway, yeah. Okay, well that was fun. We were there. Now let's go and see what else. tonight we're heading up north. You want to check out the Cocoon?
Sure.
All right, we're gonna go to the Cocoon now, guys. The Cocoon is a beautiful, beautiful nebula that's trailing this gorgeous trail of dark dust behind it. It's just stunning looking. So let's go to the Cocoon now. Oh yeah. And off we go. Okay, maybe I didn't tell it to go like I thought. Okay. There we go. Notice the telescope is starting to tilt up a little bit because its Cocoon is right there. And the trail is behind. You can see where the lack of stars are. It's not a void in the stars, as I keep saying. It's not at all. It's dark dust. Alright, let me just write this up here.
A lot of interesting questions tonight.
Yeah. Just a minute.
Cat got your tongue?
Yeah, no, I'm just checking something out. I'm writing something up here. Oh, let me see this. There we go. Okay.
Camptown ladies sing the song, doo-dah, doo-dah.
Yeah, no, I'm there. Hold on. Just getting... That's what I meant right here. I was trying to get the titling done and I messed it up. Okay, here we go. Okay, this is what I was trying to write. It was taking me forever to get it out. I'm sorry. Alright, it's the Cocoon Nebula. Let's move north with the telescope a little bit. Alright, and then we're going to move west with the telescope because we want to show you that trail of dark nebula. I won't go too far over because I want to make the Cocoon itself the main topic, main subject. This is good.
Oh, this is the fish, isn't it?
No, this is the Cocoon.
I know, but you see the dark fish around it.
Maybe. Okay. Let me see now.
If I remember right, this is yeah, you'll see like a fish's tail over to the right of it. Kind of forks.
I think you're thinking of something else.
Okay.
Well, we'll see. You might have come up with an idea that you were thinking of. Let's do 35 seconds. We're going to increase to 400 in our gain. Alright, and we're underway now with the picture for 35 seconds. Let's get out of this. We're stabilized here into the live stack. And there's our previous image. Yes, that's beautiful. That's probably already up on the server by now. Alright, so let's do this. We'll be done with that. And we'll come back with this in a minute, but I'm going to pull the title off for now. Hello, Renee Cruz. Nice to see you. Okay.
I have to think. I mean, getting on a starship, any kind of conventional propulsion, or not even conventional, but whatever could get you to the speed of light, you know, it'll take you a while to get there.
Yeah.
But it's like if you could it's almost more like teleportation or transporting or something that, you know, you step in the thing and you're transported instantaneously to your destination. You know, it's like opening a door and walking through. That would be like if you were on that photon traveling at the speed of light. It's just no time passes.
Except for the people that you left behind.
Absolutely.
Yeah, so if you go to the other side of the galaxy and back, for you it might be like a, you know, half-hour trip, because you spend you're instantaneously there. You spend 29.999 minutes, okay, and then you go instantaneously brought back. And I think what that would mean then is that everybody on the planet you left behind will have been dead and gone for hundreds of thousands of years, if not more.
Yep. See the fish's tail? That's it. That's the one I was talking about.
All right.
That dark V or U shape over on the far right.
J. Rich, you said instantaneous. Yes, you were correct. Several other people said instantaneous. Other people answered none for the time that would pass for the photon. That is also correct. Yep. Very nice. There's an interesting thing about this nebula right here. The Cocoon Nebula is called the Cocoon, obviously, for the obvious reason it looks like a cocoon, but this right here, this nebula that you're looking at right here, formed because that star right there, okay, that star right there, all right, that formed in this nebula, and when it formed in this nebula, it ionized gas out to a certain distance around it, which is what we're seeing here, all right, and that gas that it ionized is the gas that we see, all right, but the gas was mixed with dark dust, and there is dark dust around here, and as this develops, you're going to see a blue haze, a blue perimeter around here of reflection nebula. That is to say, the nebula created by dust, right? And that's something that is part of the equation too. You can start to see some of the blue as well starting to show up here, right? So this stuff is actually hydrogen gas mixed with dust in this vast trail of gas and dust in the galaxy, and the star happens to be ionizing it to make it show up.
And if you see that really dark area on the right that I call the fish's tail, there could be stars inside it. Actually, I think I see one, if it's not a foreground object, right in the middle of it, that are in their turn cooking up and turning on and eventually going to show up as more Cocoon nebulas.
That's perhaps true, yeah. So when we see stars that are vastly reddened like this, we might be seeing them as they might be objects that are inside this nebula, okay, inside this dust cloud, and that means that if they're inside the dust cloud, that their light is reddened in the same way that the sunlight traveling through more atmosphere when it's on the horizon is also reddened. So it's the same process that reddens starlight as reddens sunlight. Okay, so if we zoom way in, see these very faint red stars? Yes, they could very well be stars that are M stars that are very, very faint and red. But what about this one? What about that one? How about these two? These could very well be inside this dust nebula and be a much different color. They might actually be orange stars, you know?
Can you zoom in on that dark area to the right?
Yes?
Yeah, right in the middle of it, there's a star.
You mean this star?
No, right down in the middle. Right there to the left of your pointer.
Oh, right here?
Right there. That
Yeah.
might be a foreground object. That might be something coming to life in the middle of the cloud.
Maybe, but I mean, it does look like it's not reddened as much as the other stars, so it's probably a foreground object in my guess. But look at these faint guys here. These faint guys look like they're stars that are inside this object.
This area would be a neat target for the web, I think.
Oh, you betcha.
See into it.
But remember what I told you about the reflection nebula? Let me take this away so you can see that. Now look. Now that we've taken more frames, look around here now. This is bluish. See it? And that blue is definitely due to the scattering of high energy light from the star. All right, let's see if we can bring that out better. Yeah, that brings it out a little better. So you can see the blue now. It's very faint, but you can see it. Definite blue reflection nebula here. Now there's some in here too, but it's overwhelmed by the hydrogen emission, which is much more powerful. Isn't this great though? Looking at this object, look at that. Right here you've got some blue emission here, some blue emission here with dark nebula. Very, very complicated region. Yeah, very complicated. Let's go see if we can tease out some more data here. Pull this in. Yeah. Wow, that's something else. Yes, sirree. Hey, C&D boy says, we learned so much here, Mark. Thank you. You know what? You just got these crazy guys called astronomers that just love what they do, you know? And that's what I am. That's what Daryl is. So, hey. And we actually approach astronomy from two different perspectives. You know, mine was the research angle of learning about stars and features of the universe, and Daryl's was observational. And the things he knows about observational astronomy are not necessarily my strong suits, and the things that he knows about physics and astronomy are not his strong suit. But together, we are able to, I think, combine everything we know and spit it out there in a way that is a lot of fun. All right, Claudio asks, what's the resolution of these photos? I'll show you right up here, Claudio. Our camera is 4,144 pixels by 2,822. So that's bigger than 4K resolution. Right, so, but that's a that's pretty big. In fact, if we go, I'll give you an example. We'll go to 100% of the resolution of this. This right here, this is the native resolution. This is what it wants to be. Okay. And we go less so you can actually see all of it. Okay. But that's pretty much what we do. All right. This is really pretty. 16 frames. We'll go to 17 and move on. Actually, while it's doing that, we'll probably end up going into 18, but that's all right. Let's go see what else we can look at up in here. Well, it's an odds-on favorite. We have the flying bat. Remember that? Okay. This is pretty. So we got the elephant's trunk, the flying bat. We have the iris. I think I want to look at the iris again because it's really such a good night that I think the iris might really pay off. But I think the moon is up now.
Fairly.
Yeah. It's 10:05 there, so it's there. But let's just go check out how high it is off the horizon.
Excuse me a moment, please.
Sure thing. Alright, let's go see the moon in terms of its phase. Okay, so we're like approaching last quarter. That's good. Neato. We can still do some nebula stuff because we're using our special filters. That's awesome. Alright. So I still want to go to the iris. We're going to try that out. The iris points out some very cool things. Alright. Alright, so this is what? Are we up to 20 yet? Yeah, 20. Here we go. Alright. 20 exposures here on the Cocoon Nebula, which is that guy. Alright, and we will pause it, and I'll put in the name here. Alright, Cocoon Nebula. And we'll save it. And then save exactly as seen. There we go. Now we can clear it. End the stack. Go back to our 1 second night vision view. Alright. And go here. So you guys having a good time tonight? Pull that out. We don't need it anymore. I'm having a good time with you guys tonight. Okay, now let's go. Alright, off we go to the Iris Nebula. Here we are. Good night, Cocoon. We will leave you for another night. And then we have the iris. And there it is. Okay. Let's go a little bit to the west. And you'll see why I'm going to raise it up more. I'm glad you have a good time, guys. All right. All right, and I actually did some more work on the telescope. I collimated things so that these stars are sharp all the way to the four corners. As sharp as I could get them. They're actually really pretty now, all the way to the four corners. So we can pull things over to the edges and we'll still get beautiful imagery. Welcome back, Daryl.
Thank you.
Alright, I'm going to pull this over here.
How did you know it was me?
Because you're the only one who unmutes the mic and I can hear you in the microphone.
Oh.
I know it's you. Unless there's somebody else that you brought into your house to actually listen in on the mic. Alright. Let's
Have you had to refocus tonight?
I was just about to say that I did earlier, and I'm just going to zoom in now to check. That was the one thing I was going to check.
Okay.
I think we're okay.
I know it's getting cool down there at night now.
Yeah. It looks good. Looks good. All right. All right, so here we go. So we're going to do a 35-second shot here. And that's a 35-second shot at 400 gain. All right. And we will...
You rascal.
Yeah, right.
The moon is up now.
It is. Yep. It's approaching last quarter. It's like waning gibbous to last quarter. It's pretty close, so we're good. Okay. This is an example, unlike the Cocoon Nebula, this is an example of what happens when a star illuminates just the dust and you don't get much hydrogen emission. Okay, this is the Cocoon, the Iris Nebula. The star doesn't ionize hydrogen because it's either not in this region or it's not hot enough to ionize the hydrogen. However, the high frequency light, that is the blue light from the star, is being scattered by the dust. And so we see this embedded star, which formed here, just having its light scattered by this beautiful dust cloud. And that's something that we're going to see here developing in just a little bit. First things first, to see this better, we're going to do a color correction, get our curves aligned. Right? And then we'll do a quick analysis here this way. So now you see the dust, and it's going to become much clearer as time moves on. There's another patch right here, and you'll see more visible here very soon. This entire image is filled with tendrils of dust. So it's going to be pretty cool to watch it all develop. JSCO, thank you. That's a wonderful compliment. Izabela's in a fog. She said the fog here is so dense I can hardly see the building across the street. I believe it. Meanwhile, let's... Well,
the one with the void.
yeah, right there. Yeah. While we're waiting, I want to just go look for one other object. It's a request object. Let's see if it's something we can see. Yeah. We should be able to see it. Bubble Nebula. The other side is Cepheus. It's actually higher in the sky, so that might be a really pretty one to look at too. Alright, so this will be fun now to just watch this develop. Let's zoom in a little bit so I can show you. First of all, though, let me adjust these curves just a little bit. Okay, I'm going to take these curves and I'm going to migrate them in a little bit. You see how when you migrate them in, you can start to see knots in them. That's very important. But let's actually move this out a little bit. Tiniest amount. There we go. And now let's move in and go explore. Alright, so we have this star in the middle that formed in here. And as you notice, it hasn't ionized any hydrogen gas. Not much anyway, that's in any way dominant. And it's surrounded by all this dark dust. This is a curious opening that you see through to the stars behind. Okay, so this is blocking the stars behind, and here you see through to them. That is pretty cool. That void like that is a really neat thing. We still have some noise here.
That's noise. Some of that's where the black becomes brown from.
Yeah. I also noticed that we're picking up some wind tonight. These exposures have wind on them right now, so we stacked 9. I'm gonna start again. Or we can abandon the iris for tonight and just go to the bubble. Let's see what this next one looks like. If it looks okay, then we may continue. If it has a little shift to it, then we'll just go to the bubble. Oh no, the bubble. Huh. Well, it looks fine right now, a little bit. No, it actually has a shift to it. Look at that. Yeah, we got a shift. We also have a satellite.
It's like a tumbler.
Yeah, it might be. Bright, dark, bright, dark. Okay, you know what, guys? We'll go to the bubble because we're getting some wind, and I know you can't really see it, but if I zoom in, you can. See how the stars look stretched out? Okay, see there? Oh, look at them. See that?
Very obvious.
Yeah, so we got a major winds have picked up a little bit out there. So let's just try to go to the next one. So we'll pause it, clear it. We'll come back to this. We will definitely come back to this. Alright. Alright. Yeah, let's do our night vision view and come back here and do the Dumbbell Nebula. And there's no guarantee that it'll be perfect either, but we'll try it. Alright, so here we go. I like no more waiting. I like just going right to it.
Yeah.
There it is.
There's the salt and pepper.
You got it. Okay, let's head to the west a little bit. Alright. It's not much of a different position, so we may get some wind here as well. Let's zoom in and just see what the stars look like. Whoa, yeah, there's wind. See that? Zooming in does nothing. The telescope is, managing itself just fine. Yep, there's wind. See that?
Those are second by second shots, aren't they?
Yeah. So we're going to try something. We're going to try and we'll risk a 25-second shot. Which doesn't look like we're going to be able to get it. Oh. We're getting the cooling in the desert. Causes some wind. It's there for about an hour, then it goes away. It's alright. Okay. This was my request for Robin, but I don't think we can do it tonight. It's another Wolf-Rayet star. This is the Wolf-Rayet star right there. And it's made this bubble, and the bubble actually continues around. I'd like to get just one shot of the bubble continuing around. Oops, sorry about that. Okay. Alright.
Looks like you got 10 knot winds down there.
Yeah.
46 degrees in Wickenburg.
Yeah, it was pretty chilly out there. Alright, let's just work this one. Alright. That's pretty nice, but now you see the whole sphere. You see the whole bubble.
You say this is a Wolf-Rayet star also?
Yes, it is. We got some wind in there. The brighter stars are showing it. It's weird because the fainter stars take longer for their image to develop. The bright stars, they're almost there instantly, so they'll be dragged out, whereas the smaller stars might not look like they are. They might just have a little haze above and below. Well, it's alright. We'll see what we get.
So what is it about Wolf-Rayet stars that, I mean, they number in the hundreds that we know of, don't they?
Yeah, which means they number in the millions and the billions overall.
Well, yes, but, I mean, we see tons of O-class, B-class stars, and they don't all become Wolf-Rayet stars, do they? Or
No.
it's just a particular point in stellar evolution, or what is it about Wolf-Rayet stars that makes them Wolf-Rayet stars?
Well, it has to do with their mass and their chemical composition, you know, as part of it, I think. But as far as what they do and why, that's actually a mystery. I don't think we really know why a Wolf-Rayet star blows off its outer layers like it does. You know, something going on in the star. Maybe it's a change in the radiative regions of the star, and the way that radiation is being emitted. You know, many stars have convection layers on the outside. Maybe the convection layers in, say, a star that became a red giant or a giant star, maybe that caused something. I don't know. I mean, I just don't know. I never studied Wolf-Rayet stars extensively, other than to just understand their basic chemical properties. Because at the time, you know, no one really knew why, and they still don't really know why a Wolf-Rayet star does what it does. Well, I can see how on a nice night where we don't have any wind, this whole bubble region will really shine beautifully. Then we have that cluster up there. We have this other nebula right here. We have the lobster claw down here.
The one up at the upper right.
Yeah.
What, I forget. It has a name. What is that?
That's not the spider or the fly, is it?
I don't remember.
This is the lobster claw down here, the beginning of the lobster claw.
Is that the Little Lagoon Nebula?
Let's go find out. Let's go find out. First of all, we're talking about this guy right here. Yeah, what is it? It is. Yeah, it's the Northern Lagoon.
Northern Lagoon, okay.
It's another stellar nursery, just a little further away. That's what the lagoon would look like if it was another, I don't know. Let's see, what would it say this was in distance? It said, Well, it gets its redshift, but it doesn't give its distance. Interesting. I mean, you can calculate it, but I think you got to get the answer in parsecs, and you got to convert to light years. Not bad. You can see the lobster claw developing down here. So there's the Bubble Nebula for Robin Curtis. She asked for it.
Heater just kicked on. Can you hear it?
No. Mine's been on the whole time. Okay, it looks like we're still getting... Yeah, we're getting wind. But by stacking, you kind of mitigate some of that error. But there's the Wolf-Rayet star, and this is the area that is really interesting. Wow, sneeze. That's new. Alright. Let's see if there's something else we can look at while we're in this region. It may not be, because the wind's going to kick in probably for the next hour or so.
And in a general sense, again, what is it Wolf-Rayet stars do?
The Wolf-Rayet stars have the core and the outer envelope of materials that they were made with, and they're probably on the order of 20 to 30 times the mass of our sun. And in general, what they'll do is they, for some reason, will completely kick off their outer layers, leaving that hot core still fusing. But what that does is it robs the star of the ability to dredge material from that envelope down into the core again to continue fusion. So it shortcuts you to supernova. Once it's expelled, it's not coming back.
In a sense, then, it's like what I said earlier, that nowadays they think some planetary nebulas actually come from Wolf-Rayet stars. Similar sort of process with, typically I know a planetary nebula comes from a sun-like star. When it gets old and goes to its red giant phase and starts sloughing off its outer layers, its outer atmosphere. Is that kind of analogous?
I don't know, because I think that the actual violence with which Wolf-Rayet star expels that outer envelope is different from the violence or lack of violence of the sloughing off. So we talk about the planetary nebulas as sloughed off outer layers. It doesn't sound very violent. It sounds like they just got so big they drifted away from the star and kept going. That could be what's happening with Wolf-Rayets, except that the Wolf-Rayet star has a lot of very high radiation pressure, a lot of stellar wind, extraordinary stellar wind. So it's going to be blowing this stuff off at a very high rate of speed. In fact, that might be the reason that they do what they do, is because they have an extraordinary high stellar wind, and that would make sense to me. Okay, we did 20 here. I'll just allow us to do those. And we'll call it the Buble Nebula.
I see the dark spiderweb lanes in the lower left part of that image.
Down here?
Yeah, that I comment on sometimes.
Yeah.
Looks like curved dark lines.
Yeah.
Between rows of stars.
Okay. Go ahead.
I'm sorry. Hello, Nescabed. Yes, that's exactly what they are. The dark areas are dark nebulae, dust, clouds.
Yeah, and that's good. Thanks for coming along. Good to see you. Yeah, and what Nescovic did is and what Hedrick does too. Very good. If you want to ask questions, you're allowed to put them in all caps. We don't take it as yelling. We take it as, hey, look at me, I got a question. So that's equivalent to raising your hand, I guess. So that's fair to do in a chat. But don't yell with it. You're just asking questions is very good. Okay. Well, that's not so bad. You know? Let's go see if we can do one more.
Those dark lines lower left, that just looks like black spaghetti or something.
I just think you're just seeing things. No, I don't.
Don't say that. I see them so often, especially up in this part of the sky.
Yeah.
Cepheus, right?
Yeah. Okay. This is gone. We're gonna go here and do our 1 second night vision mode.
See, Ramos, I'm sorry, I know you've asked that several times. Stars have any relation with earthquakes? I suppose you could say, insofar as a star and a planet, you know, having tidal effects on the planet could possibly relate to earthquakes, certainly.
But certainly no other stars.
I'm sorry?
Certainly no other stars would have as much impact on Earth as our star.
Oh, sure.
But I will say this. We did have an event recently that did cause changes in the Earth's mantle, and that was caused by a stellar event elsewhere. Those changes were small, but they were still measured, so it's possible that in some way that could happen.
What are you talking about? What in particular?
I think it was
Not that gamma ray burst, was it?
I think it was, and that actually caused changes in the current flows inside the Earth. Isn't that what it was?
That was like 2 billion light years away. I remarked on it at the time. They detected ground effects, subsurface effects from a gamma ray burst, soon to be a supernova or something of the sort.
That's right.
From 2 billion light years away.
Yeah.
And it affected the Earth, ground currents, I think it was.
Yeah.
And it also caused atmospheric effects.
Yeah.
From 2 billion light years away.
Exactly so. And that was one of the things that I thought was pretty interesting about the entire ordeal. Okay.
That's kind of scary to think about.
Yeah. Because you can't stop it. You know? Can't stop it.
Yep.
Okay, this one is the cave. And we will do this 30-second exposure. And we'll try it. There it is, the bubble left over. It's not as sharp as it could be because the stars are a little bit elongated from wind. But this will be the final object for the night. So we'll clear this now and get the cave to show its beauty to us. Come here until I have you ready. And the cave looks like... Okay, that's good. So far, so good. That looks good. That light color you see in there is due to the moon. We have the filters that can handle that, but we can get rid of it. But we do see it happening, so we will have to deal with it. And guys, as this is developing, notice these down here. See these reddish things right here? Okay, those are objects that are called Herbig-Haro objects. Herbig space Haro. Herbig-Haro objects. The fertile young stars are being born there. So you'll see it as we develop further. We've done 3 so far. Let's see where it wants to take us for color correction. Let's do that. Alright, and let's do this. Oh yeah, look at that, huh? Yeah, do give us some thumbs up, will you? We just wanna be your observatory. That's who we are right there. SkyTour LiveStream, yeah. No one else is doing a live deep sky observatory like this. No one. There's no one on the planet doing this. I just love it. Claudio, you heading out? Thank you for coming along. Really enjoyed having your company with us tonight. Thank you so much, and please come again. Yeah. Claudio, you feel like a friend now, so this is cool. Is that Alana saying goodbye, or is that Alana saying goodbye to us because she's leaving? GRBs are gamma ray bursts. Daryl's using shorthand.
Sorry.
Well, it's less to type. Oh, look at this beautiful nebula. See this dark nebula developing over here? There's even more over here that we haven't captured yet. But we're catching the new young stars that are forming down here. The Herbig-Haro objects. Let's go check out whether we can eliminate some of the noise as we just... There we go. Oh, it's beautiful. Zoom in. 7 stacked, we can zoom in a little. This is a beautiful area. This is a beautiful hydrogen ionized location. Carolee, good evening to you as well. I'm in Connecticut and Daryl is in Colorado. And there are people here from Australia, Bangkok, Chile, and many other countries. And the country of Colorado. I'm kidding, of course. The state of Colorado. Yeah, Carolee, the night has been nice. We've been looking at some great things. And they're up in the database. You can find it right here, SkyTourLive.com. See that right there? That right there, that's our portal to get to all of our data. You scroll down, and the next pick you select, it takes you to the database, which is free. You can download any image we captured tonight, any night as a matter of fact, and use it as your wallpaper or whatever, and they come out really pretty. Thank you, Izabela. She just put up the link right there for SkyTour Live. Alright, we're up to 11, and slight wind effects here, but we're okay. Robin Curtis mentions, I saw an article recently talking about new research showing volcanoes are linked to most major extinction events they think could actually be the causes of the extinctions. I know in one particular case, the Permian extinction 252 million years ago, it looks like a volcanic eruption in the location known as the Siberian Traps today is, yes, exactly, Daryl, is a location where a volcanic eruption occurred. It was like a flood basalt where the lava would start up at like fissures, long cracks, and they filled in, and a cap was formed on top of that lava that didn't allow more to come out. So the lava spread sideways into dikes and volcanic dikes, and those actually kept going out and radiating away from the center of all this. It was a major eruption, but it was plugged, so it went out sideways underground, and as it encountered organic material, it fried it, and so a lot of carbon-based stuff was in there, and a lot of carbon dioxide was liberated during that moment, in those moments. So it went out for I don't know how many miles, okay, but what ended up happening was the lava cap couldn't contain it, and after a number of months or whatever of eruption, the edges of that lava field were the cap was thin enough so that the lava could make it to the surface, and it brought with it all the gas that it had made all along the way underground under high pressure, and that gas amounted to many gigatons, many billions of tons of carbon dioxide. Now, when you think about it, how much is a ton of carbon dioxide? Now imagine billions of tons of carbon dioxide. You just think the atoms weigh almost nothing, right? And just imagine gigatons, so billions of gigatons of carbon dioxide flooded into the atmosphere in just a very short time. Maybe a week, maybe 2 weeks, I'm not sure. And in that time, and because of that flooding of CO2 into the atmosphere, it turned out that the temperature of the Earth rose by 21 degrees Celsius in that time. And that was enough to raise the temperature of the oceans. When the oceans are higher temperature, oxygen doesn't like to stay in the water. Photosynthetic bacteria, known as plankton, that make the oxygen, they can't survive. And it ended up causing a major extinction event of the oxygen-producing creatures on the planet, which are the most important ones. So 96% of all life on Earth died at that because of that eruption. And but the life forms that were hit the hardest were those that would have become mammals, like us. So they basically effectively went into hiding. And when they went into hiding, they remained in hiding because the next creatures that rose to prominence were the dinosaurs. And because of that Permian period extinction, this led to the age of the dinosaurs. And the age of the dinosaurs was cut short by the Chicxulub asteroid impact. And that Chicxulub impact is what caused a domino effect of the plant eaters losing their food supply, and thus the meat eaters lost the plant eaters, and then everything else. So that caused an extinction event, and a lot of niches opened up. A lot of life niches opened up that were formerly populated by dinosaurs. And guess who filled them? The creatures that would become mammals, that were hiding in the background and just relegated to second-class status, now just proliferated and filled those niches. And that started that long chain of evolution that led to hominids like Lucy, Australopithecus afarensis, and Homo habilis, and Neanderthal, and Cro-Magnon, and so forth, all the way to Homo sapiens sapiens, which was us. So we turned out exactly the way we did because of those extinction events. Hey there, Rascally Rabbit. Good to see you. Okay, we're at 21 stacked for the cave. Oh yeah, look at that. Wow. That's pretty. Oh yeah. Holy cow. That's pretty, huh? Let's back out and check out the Herbicaros. Here they are, down here. Here it is, folks. Take a look at some nice young hot stars that just formed in the last few tens of thousands of years. Yeah. Neato. Wow. That's something else. Alright.
We talked recently, I mean, this is the Cave Nebula. Is there also a Wolf Cave Nebula?
Yeah, we talked about that, didn't we? Yeah. You can almost see how this is three-dimensional, it seems, you know what I mean?
Oh, yeah.
I don't know if it really is, what we're seeing. I mean, it's just the perception of our eyes. Wow.
Well, I've mentioned before, like when we look at that bright area on the Pelican Nebula,
Yes.
or when we see that wall on the near the Horsehead
Mm-hmm.
in Orion, that we may be seeing such a thing almost edge on, you know,
Yeah.
as far as three-dimensionality goes. That bright red spot, that line could be coming straight toward us.
Yeah.
We're seeing it sort of edge on.
Okay, we have 26 stacked here. We're going to pause it here. And we'll save it as the Cave Nebula, as it's listed up there. I messed up one tonight, and that was a North American Nebula. I'll correct it. And then I'm going to save exactly as seen. Very good. Well, there it is, folks. What do you think? Let's just pull this over here for a minute and explore this for just a sec. Wow. We got a reflection nebula over here. We have this beautiful dark nebula in here. Really pretty. We've got this bluish haze around the red. This is a reflection nebula. You can see the blue color here. There's dust in here that's being made into reflection nebula because it's scattering the blue light from the hot stars. And then we have the hot stars ionizing hydrogen, making it red. I mean, the two main colors of the universe are red, hydrogen emission, and blue, which is the scattering of starlight by dark dust. Excellent.
Huh. It's not the Wolf Cave Nebula, it's Wolf's Cave Nebula with the WOLF
E?
apostrophe S.
Okay.
Wolf was German astronomer Max Wolf.
Okay. Well then, wait. Isn't that spelled WULF?
Well, they have it as WOLF.
Okay. Alright. Well, that's beautiful. Alright, guys. Well, there you go. That's our last object for the evening, the Cave Nebula. I hope that it met with your satisfaction. It certainly met with mine. It looks so cool. This is a very good night. So, this is going to be up there in just a second. I'm going to save it again, even though I already saved it. I'll save it one more time.
Well, you're sneaking up on me with these last objects now.
Nope, I said this was our last object about 10-15 minutes ago.
Oh.
Haha. Maybe you were away putting down your teacup.
Or something like that, yeah.
Yeah.
Probably.
So there we go. So this
Nice
shows you all the other stuff that's out here that we can draw out with processing. Look at the complexity here. These diagonal streaks I'm going to be getting rid of if we replace the camera. So that's really cool. Nice. We can really go to town on those if we want to. All right. So there we go. All done. Excellent. Wow. Not bad at all. I'm very, very pleased. Very, very pleased. It was such a good night.
Yeah, it's a great stream.
Yeah. So anyway.
Good night, everybody.
Yeah, I hope you guys have a good night. Well, there you go. You hear that music, you know what it means. We'll talk to you again. We will see you again. And remember, when you go outside, keep looking up because you never know what you'll see. So we'll talk to you as early as tomorrow, maybe the night after. Good night, everybody.
all.
See you later.